Well, thank you so much for coming this day. This is the last day of our meeting. The first talk this day is DG Enhancing of Requirements. The speaker is Valente Santiago Vargas from Universidad Nacional Autónoma de México. Thank you so much, Valente, for coming.
Entonces, mi plática va a ser en español. Ok. Entonces, a ver. No quiere, sí. Para que pica la presentación. Ahí está. Ok. Entonces, pues yo les voy a hablar sobre DG Enhancing of Requirements. Es mejoramiento de requirements sobre categorías DG, sobre categorías diferencialmente graduadas, diferencial graduadas. Entonces, este es un trabajo que tengo con mi alumno de doctorado, Edgar Omar Velasco, ¿sí? De la facultad. Ok, entonces, pues voy a hablar un poco de qué son las categorías diferencial graduadas. Listo. Ok, ok, entonces, pues, ¿para qué queremos categorías diferenciales graduadas? Pues bueno, como ya Juan Omar habló en su curso, pues bueno, primero, las categorías diferencial graduadas tienen que ver con categorías trianguladas. Las categorías trianguladas fueron definidas por, ya lo dijo Juan Omar, por Grothendieck y su alumno de doctorado Verdier, ¿sí? Y bueno, Grothendieck en 1958, en su plática en el Congreso Internacional de Matemáticas, dijo que faltaba desarrollar toda una teoría de álgebra homológica para desarrollar toda una teoría de cohomología y homología de variedades algebraicas, ¿sí? Entonces, esa herramienta que todavía no estaba, se la dejó a su alumno. Vale. Explícale, por favor. Sí. Entonces, se la dejó a su alumno. ah, Adelante. A su alumno Verdier, ¿sí? Y entonces, su alumno, en su tesis de doctorado, desarrolla todo lo que son las categorías trianguladas, ¿sí? Y en particular las categorías derivadas. Ok. Entonces, bueno, yo no voy a repetir los axiomas que dio Juan Omar de categoría triangular, pero hay un axioma que nos importa aquí, que es el axioma TR3, que nos dice básicamente lo siguiente. Si nosotros tenemos una categoría triangulada y tenemos dos triángulos distinguidos, ¿sí? Y tenemos dos pares de morfismos tal que este cuadrado conmuta, entonces el axioma nos dice que podemos completar ese morfismo con un morfismo gamma de tal forma que tengamos un morfismo de triángulos. Entonces el axioma pues, T3 nos dice eso, no TR3, de que dado dos triángulos distinguidos y dos morfismos alfa y beta de tal forma que este cuadrado conmuta, entonces existe un morfismo gamma tal que se puede completar un morfismo de triángulos, ¿sí? Entonces este axioma pues nos recuerda más o menos a los que han trabajado en categorías abelianas como la propiedad universal del cokernel, ¿no? El Z se puede pensar como el cokernel de F y el Z' como el cokernel de F', y la existencia de este gamma lo que nos está dando se da por la propiedad universal del cokernel. En categorías abelianas, pues se demuestra que ese morfismo gamma es único y en categorías trianguladas no se pide que sea único, ¿no? Entonces ese es un gran problema que tienen las categorías trianguladas, la no unicidad de estos términos. Esos términos se les llaman los conos, ¿sí? Y entonces, Bueno, entonces aquí vienen en juego las categorías de G, ¿sí? Ay, ¿le picas? Ok, entonces, pues como esa noción no es funtorial, los conos no son funtoriales, entonces mucha gente empezó a creer que esa no era la noción correcta que se necesitaba. Y bueno, dentro de ellos, pues, por ejemplo, Gelfand y Manning pensaban eso. Y entonces mucha gente empezó a trabajar en qué podría ser la noción correcta para corregir ese problema. Entonces, una de las primeras cosas que fueron propuestas fue el mismo Grothendieck quien la definió. Eh, una de las propuestas para resolver el problema de la no funcionalidad de los conos es la teoría de derivadores, construida en este trabajo de Grothendieck, Pursuing Stacks, ¿sí? Entonces, esa es una posible forma de arreglar el problema. Otra forma es de la que yo voy a hablar ahora, hablar sobre las categorías de G, o más generalmente sobre las categorías infinito uno, categorías estables, ¿sí? Entonces, las categorías de G resulta ser que son un ejemplo particular de infinito uno, categorías estables, pero yo voy a hablar más en particular sobre esto, ¿sí? Ok. Entonces, las categorías de G de diferencial graduada, pues en realidad ya tiene mucho que surgió en el 65 en un artículo de Max Kelly, ¿sí? Pero resulta ser que durante mucho tiempo las categorías de G no las estudiaron en sí mismas, sino que fue hasta que en 1991 dos matemáticos rusos, Bondal y Kapranov, utilizaron a las categorías de G para remediar el problema de la no funcionalidad de los conos, ¿sí? Ellos estaban estudiando en categorías de gavillas coherentes sobre variedades proyectivas, ¿sí? Entonces, ellos querían arreglar ese problema de cierta forma, ¿sí? Y, y bueno, y entonces ellos definieron lo que es un DG enhancement o un mejoramiento de una categoría triangular sobre una categoría diferencial graduada, ¿sí? Entonces, ¿qué es eso? Entonces, nosotros tomamos una categoría triangulada, T, y tomamos una categoría de G. En un momento voy a dar qué es una categoría de G, ¿sí? Una categoría de G pero triangulada. Esto lo que quiere decir es que hay una construcción de tal forma que a esta categoría de G se le puede asociar de forma canónica una categoría triangulada, ¿sí? Pero bueno, entonces tomamos una categoría de G que sea pretriangulada y decimos que esta categoría de G es un mejoramiento de la categoría triangulada T si la categoría triangulada T es la categoría homotópica de la categoría de G, ¿sí? Entonces se puede pensar que la categoría triangulada es un tipo de sombra de la categoría de G, ¿sí? O sea, hay un ambiente más grande que es una categoría de G y al calcular la categoría homotópica de esa categoría de G, recuperamos la categoría triangular, ¿sí? Y entonces resulta ser que gracias a que la categoría triangular T es la categoría homotópica de una categoría de G, el, la no funtorialidad esta eh, no es no es que se vuelva única, sino que se vuelve única salvo homotopía. Entonces, o sea, hay una forma de arreglarlo, pero salvo homotopía, ¿sí? Ok. Entonces, para eso se utilizan las categorías de G, ¿no? Para mejorar categorías trianguladas. Y bueno, entonces, ¿qué es una categoría de G? Para eso, pues necesito definir primero algo que son ciertos módulos diferenciales graduados. Entonces voy a empezar con un anillo conmutativo arbitrario, un anillo conmutativo con uno, y un módulo diferencial graduado es un módulo que se descompone como una suma directa de subgrupos, ¿sí? De tal forma que hay un endomorfismo de M en M de grado 1, tal que la composición de dos ellos es cero. Esto de grado 1 lo que quiere decir es que manda la componente de grado n en la componente de grado n más 1, ¿sí? Ok. Y entonces, bueno, con esto podemos formar una nueva categoría que son la categoría que va a tener como objetos a estos módulos, los módulos diferencial graduados, ¿sí? ¿Y cuáles van a ser los morfismos? Entonces, dado dos módulos diferencial graduados, M y N, entonces los morfismos van a ser de nuevo, va a ser de nuevo un módulo graduado, ¿sí? Donde los morfismos, donde los morfismos de grado N, de M en N, son exactamente los morfismos que mandan la componente yésima de M en la componente yésima I más, en la componente I más N de N, ¿sí? Entonces, esa es la componente yésima de este morfismo, del conjunto de morfismos de M en N, y entonces al conjunto de morfismos se le da otra vez estructura de módulo graduado, ¿sí? Ok, y bueno, ya tenemos un módulo graduado, y también le podemos dar, le podemos dotar una diferencial al conjunto de morfismos. Ujú. Entonces, yo tengo un módulo graduado, también le puedo dar una diferencial y se da por esta regla, ¿sí? Tomo un morfismo acá de cierto grado, un morfismo homogéneo de cierto grado, ¿sí? Entonces, le puedo aplicar primero, puedo hacer la composición de alfa con la diferencial del módulo n, y también puedo primero aplicar la diferencial del grado del módulo m, y luego hacer la composición con alfa, y luego aquí hay un signo, y este símbolo lo que quiere decir es el grado del morfismo alfa, ¿sí? Entonces, se puede demostrar que esto mm, define una diferencial sobre el conjunto de morfismos, ¿sí? Y bueno, también dado dos módulos diferencial graduados, también al producto tensorial se le puede dar estructura de módulo diferencial graduado, ¿sí? La componente yésima, la componente enésima del producto tensorial va a estar dado de esta forma, como ya más o menos había explicado Juan Omar, y la diferencial, pues la diferencial del producto tensorial, pues involucramos tanto la diferencial de M como la diferencial de N, y va a estar dada por esta fórmula, ¿sí? Y se demuestra otra vez que eso al producto tensorial le da, eso define un morfismo de grado 1, y la composición de dos de, consecutivo nos da 0, ¿sí? Ok, y entonces resulta ser que el ejemplo primordial de categoría DG es esta. Estas, los módulos diferencial graduados junto con estos morfismos forman una categoría DG. ¿Sí? Ok, y entonces, ¿qué es una categoría diferencial graduada? Entonces, una categoría diferencial graduada, pues va a ser una categoría donde ahora, el conjunto de morfismos entre un objeto y otro objeto ya no solo va a ser un conjunto, sino ahora se pide que sea un módulo diferencial graduado sobre K, ¿sí? Sobre un anillo conmutativo. Y además se va a pedir que la composición, entonces este es un módulo diferencial graduado, este es un módulo diferencial graduado, puedo hacer producto tensorial, puedo obtener un módulo diferencial graduado, ¿sí? Entonces lo que se pide es que la composición sea un morfismo de grado cero. ¿Sí? Ok. Y entonces, bueno, un morfismo de grado cero que conmuta con diferenciales. Entonces, con esto, básicamente, lo que se demuestra es que la diferencial satisface algo que se llama la regla de Leibniz. ¿Sí? Ahorita voy a dar un ejemplo de eso. Ok. Y entonces, para los que saben de categorías enriquecidas, en realidad, una categoría diferencial graduada, en realidad es solamente una categoría enriquecida en la categoría de complejos, ¿sí? Porque los podemos pensar como complejos, ¿sí? Ok. Y entonces, bueno, ejemplos de álgebras diferencial graduada, de categorías diferenciales graduadas, pues la más sencillita es, pues, cualquier álgebra graduada diferencial que es una álgebra que satisface la regla de Leibniz, ¿sí? Se puede pensar como una categoría diferencial graduada con un solo objeto. Entonces, las álgebras diferenciales graduadas son ejemplos de categorías de G, solo que con un único objeto. Y bueno, y ya les había hablado del ejemplo este, que es el ejemplo de categoría de G, ¿no? Sí, primordial. Ujú. Ok, entonces, bueno, entonces ya que nosotros sabemos nuestras categorías, ahora necesitamos definir cómo las vamos a relacionar. Entonces, como nuestras categorías tienen más estructura, pues los funtores que nos relacionen en esas categorías, pues les vamos a pedir más estructura, ¿no? Entonces vamos a pedir funtores graduados. Entonces un funtor graduado va a ser un funtor de tal forma que recordemos que el conjunto de morfismos entre dos objetos es un módulo graduado, entonces podemos hablar de la componente homogénea de grado n. Entonces lo que pedimos básicamente es que la componente homogénea de grado n vaya a dar a la componente homogénea de grado n, ¿sí? Entonces esos son los funtores graduados, pero recordemos que estos no son solo módulos graduados, sino que vienen dotados con una diferencial, y entonces en realidad los funtores que nos van a interesar van a ser funtores graduados en ese sentido, que además conmutan con las diferenciales. ¿Sí? Y entonces esos van a ser los funtores que nos van a interesar, los funtores de G. ¿Sí? Ok. Y bueno, entonces ya que tenemos cómo se relacionan dos categorías de G a través de funtores de G, podemos hablar de las transformaciones naturales entre funtores de G. Y resulta ser que otra vez queremos que el conjunto de transformaciones naturales entre dos funtores de G vuelva a ser un módulo diferencial graduado. Entonces, necesito definir la componente homogénea de grado n de mi conjunto de transformaciones naturales, ¿sí? Y entonces, aquí es lo que, esto es lo que hago. Ahí, ¿sí? Aquí es, entonces, quiero definir el conjunto de transformaciones naturales entre dos funtores diferencial graduados. Entonces, va a ser de nuevo un módulo diferencial graduado, donde dignat entre f y g, ¿sí? Van a ser más o menos van a ser, como conocemos, pares de morfismos en la categoría, si F y G van de C en D, van a ser van a ser morfismos que van de F de X en G de X, que además son de grado N, y además el chiste acá es que como bueno, aquí lo que pedimos es que este diagrama conmute salvo un signo, ¿no? ¿Sí? Entonces, si solo fueran morfismos de grado cero, pues solamente obtendríamos las transformaciones naturales que conocemos, pero como queremos la cosa enriquecida en módulos diferenciales graduados, entonces pedimos que esto conmute algún signo, ¿sí? Y bueno, entonces se demuestra lo siguiente. Bueno, entonces podemos hablar de, dado dos categorías de G, podemos hablar de la categoría de funtores de C en D, ¿sí? Donde los objetos van a ser los funtores de G de C en D y los morfismos van a ser las transformaciones de F y G. ¿Sí? Y resulta ser que otra vez queremos, ya a esto ya le doté de módulo graduado, entonces queremos darle una diferencial, y la diferencial se define puntual. Sí, entonces aquí está la fórmula, la diferencial de una transformación natural se define de manera puntual, y bueno, se demuestra que eso dota una estructura de módulo diferencial graduado sobre el conjunto de transformaciones naturales, y con esto lo que se prueba en realidad es lo siguiente, que si tomamos dos categorías diferencial graduadas pequeñas y consideramos la categoría de funtores de G de C en D, eso vuelve a ser de nuevo una categoría diferencial graduada, ¿sí? Um, Esto es importante porque, por ejemplo, en el caso de categorías abelianas, se vuelve a satisfacer esto. Si tomamos dos categorías abelianas, entonces la categoría de funtores aditivos vuelve a ser una categoría abeliana. El chiste es, el chiste es que en categorías trianguladas eso no pasa. No pasa que si tomamos dos categorías trianguladas, el conjunto de funtores entre dos categorías trianguladas, funtores que preservan la estructura, vuelva a ser una categoría triangulada. O sea, eso no pasa. ¿Sí? Y entonces, o sea, estos tienen estructuras que mejoran a las categorías trianguladas, ¿no? Ok. Y entonces, dada una categoría de G, yo puedo hablar de la categoría de módulos sobre esa categoría, ¿sí? Puedo hablar de un módulo izquierdo sobre esa categoría de G, entonces no va a ser más que un funtor de G de esta categoría, en esta categoría que también vuelve a ser una categoría de G, ¿sí? Entonces, los módulos izquierdos van a ser funtores covariantes, ¿sí? Y análogamente se pueden definir los módulos derechos como los funtores contravariantes de G, así, que van de COP en Digimod K, ¿sí? Ok, y entonces, bueno, con esto podemos hablar de la categoría de módulos Digimod C, de módulos diferencial graduados sobre la categoría C, ¿sí? Que tiene por objetos a lo que ya dije anteriormente, y los morfismos entre dos módulos van a ser transformaciones Digi, transformaciones naturales, ¿sí? Ok. Bueno, entonces, ahora les voy a hablar sobre los recolements y bueno, cómo obtenemos un recolemont. Entonces, dado una categoría diferencial graduada, puedo hablar de de un ideal diferencial graduado. Un ideal diferencial graduado de la categoría C no es más que un subfuntor diferencial del funtor OM, ¿sí? Y eso lo que quiere decir básicamente es que para cada par de objetos A y B, el conjunto de morfismos de A en B va a ser un submódulo diferencial graduado del conjunto de morfismos de A en B, y además va a ser cerrado por composición tanto a izquierda y a derecha. Es decir, si yo tengo un morfismo que pertenece al conjunto, al ideal que va de A en B, ¿sí? Y yo compongo a la izquierda y a la derecha, entonces la composición vuelve a quedar dentro del ideal, ¿sí? Ok, y entonces con esto, bueno, nosotros se tiene esa noción y podemos hacer una construcción como sigue. Dada una subcategoría diferencial graduada de C, podemos hablar de los morfismos que se factorizan a través de objetos en B, ¿sí? Entonces nos vamos a fijar en los morfismos de grado N que van de C en C', que se factorizan a través del objeto B, y esos van a ser los que vamos a definir aquí, ¿sí? Y, y cuando hago la suma directa de todos ellos, pues lo que obtengo es un módulo diferencial graduado, y lo que se demuestra es que este es un ideal de G de la categoría C, ¿sí? Y entonces, con eso, pues lo que podemos hacer es la categoría cociente. Entonces tomo un ideal de G de C, puedo formar la categoría cociente y resulta ser que la categoría cociente vuelve a ser una categoría de G. Los objetos son los mismos y el conjunto de morfismos en la categoría cociente entre el objeto A y el objeto B está dado por este cociente de módulos diferencial graduados, ¿sí? Entonces, vuelve a ser una categoría de G y bueno, la composición pues se define como se debería, ¿sí? Y el chiste acá es que tenemos un funtor de G, que es la proyección canónica, ¿sí? Y entonces, este funtor de G, lo que resulta ser es que con eso podemos tener un funtor entre sus categorías de módulos, ¿sí? Entonces, si yo tengo mi funtor de G, de que va de C en el cociente, que me equivoqué, aquí debe ser módulos diferencial graduados, ¿sí? Y yo tengo un módulo diferencial graduado sobre la categoría cociente. ¿Qué es un módulo diferencial graduado sobre la categoría cociente? Pues no es más que un funtor que va de la categoría cociente en módulos diferenciales graduados. Entonces, cuando yo hago la composición de este funtor F con G, lo que obtengo es un funtor que va de C en en módulos diferenciales graduados. Y entonces lo que obtengo es un funtor que va de la categoría que va de la categoría de módulos diferenciales graduados sobre la categoría cociente a la categoría de módulos diferenciales graduados sobre C. Sí, y resulta ser que esto se demuestra que ese es un funtor fiel y pleno, ¿sí? Y ya, ya en un momento acabo. Entonces, ok, y entonces, ¿qué es un recolemont? Bueno, es una palabra en francés que se puede traducir como acoplamiento o pegado, ¿sí? Y entonces aquí la noción de recolemont fue introducida por Beilinson, Bersen y Delis, ¿sí? En su estudio de gavillas perversas. Ellos trataban de axiomatizar ciertos funtores que había definido Grothendieck en geometría algebraica, ¿sí? Y entonces es cierto tipo de pegado de categorías. Ahorita voy a explicar cómo es ese tipo de pegados de categorías, ¿sí? Y bueno, surgió en geometría algebraica con estos autores y resulta ser que en teoría de representaciones de álgebras también surgen naturalmente los recolements en el estudio de las álgebras casi hereditarias, en el estudio de categorías de peso máximo. Ok, Entonces, ¿qué es un recolemón? Entonces, un recolemón, pues tenemos tres categorías, C, A y B, ¿sí? Que pueden ser categorías diferencial graduadas, pueden ser trianguladas o pueden ser abelianas, ¿sí? Entonces, un recolemón se puede pensar como una sucesión así de funtores, de tal forma que estos dos funtores forman un par adjunto, o sea, estos funtores forman una terna adjunto de funtores, es decir, este pi estrellita arriba es funtor adjunto izquierdo de pi estrellita abajo, y este pi estrellita abajo es funtor izquierda de pi signo de admiración arriba, análogamente con estos, ¿sí? Y además lo que se pide es que el kernel de este morfismo, de este funtor, que va de A en B, sea la imagen del funtor pi estrellita abajo. Y lo que se pide es que este funtor que va de C en A sea un funtor fiel y pleno, y los extremos que van de B en A y de B en A, estos dos extremos, también sean fieles y plenos. Entonces, a lo mejor en un dibujito lo podemos ver de esta forma. Entonces, tenemos eh, esta sucesión de funtores. Este funtor es un funtor fiel y pleno, también este que va de acá para acá, esto de acá va acá para acá. Por eso que los dibujé más o menos así, ¿sí? Podemos identificar estos dentro de esas categorías. Y bueno, y entonces el chiste que nosotros demostramos con Edgar es lo siguiente. Es que si tomamos una categoría de G y tomamos una B, una subcategoría diferencial graduada cerrada por coproductos, y formamos el ideal ese que les definí hace un ratito, y entonces y consideramos el funtor proyección y consideramos el funtor inclusión de la categoría B en C, entonces esos funtores me inducen estos funtores que van de aquí, que pueden empezar como cambio de categorías, y lo que se demuestra es que tuvimos un recolemón a nivel de categorías diferencial graduadas. ¿Sí? Y bueno, el chiste es que se demuestra, bueno, ahí está el dibujito, lo que se sabe es que cuando tomamos los cerociclos de esta categoría diferencial graduada, los cerociclos de esta diferencial graduada y los cerociclos de esta diferencial graduada, entonces resulta ser que los cerociclos forman categorías abelianas. Entonces, lo que obtenemos es calculando los cerociclos, obtenemos un recolemón a nivel de categorías abelianas, y cuando calculamos la categoría homotópica, también obtenemos un recolemón. Sí, entonces, nada más que aquí la categoría homotópica es una categoría triangulada. ¿Sí? Entonces, pues se puede pensar que el recolemón que nosotros obtuvimos es un tipo de mejoramiento de cierto tipo de recolemons a nivel de categorías trianguladas, ¿no? Bueno, una pregunta que se puede hacer es, si uno tiene un recolemón de categorías trianguladas, ¿bajo qué condiciones admiten un mejoramiento un mejoramiento de categorías de G? Pues en eso estamos trabajando, y bueno, eso es de lo que les quería platicar. Luis.
Comments, questions, preguntas, comentarios para Valente.
Entonces obtienes tres recolemons, ¿verdad? Al
Sí.
final. Y ¿podría ver la lámina donde defines el ideal respecto a la subcategoría?
Sí, a ver. Sí.
Ah, sí, ok. No, no,
Sí, sí.
vale. Ya, gracias.
Sí, listo.
¿Otra pregunta, comentario?
¿Estás pensando en un contexto específico, o sea, donde este aplique?
¿Qué qué?
¿Estás pensando en algún contexto en específico donde aplique que puedes construir este ideal y, no sé, te da algo, no sé, familiar?
Sí, o sea, estoy pensando, por ejemplo, sí, o sea, por ejemplo, podemos pensar en, pues lo de las categorías estables, ¿no? O sea, que son, pues podemos tomar, o sea, tratar de obtener, si tenemos recolemons a nivel de categorías estables, digamos, de categorías trianguladas, ver si cuando esos recolemons hay un mejoramiento a categorías de G de esos recolemons. Pues ya ves que las categorías estables son pues, más o menos así, módulo proyectivos y cosas así, ¿no? O sea, este tipo de ideales pues, son los más conocidos, los que utilizan mucho en representaciones, ¿no?
Está revisando, no necesariamente
Sí.
Y bueno, la otra pregunta quizás es un poco más vaga, pero cuando tienes un recomo de categoría, de infinito categorías estables,
¿Perdón qué?
cuando tienes un diagrama de este estilo, ¿no? De infinito categorías estables y las categorías son compactamente generadas, entonces lo puedes ver, pues es como un sí solo sí, ¿no? De la categoría homotópica, una vez que ves la categoría homotópica, entonces tienes un recomo de infinito categorías estables. Me pregunto si esto también es cierto para categorías de G.
Ya,
O sea,
ya.
la cosa es que no tienes quizá tanta estructura, ¿no? Porque no estás asumiendo que las categorías, es por eso pregunto.
Sí, ujú, ujú. Digamos, en el contexto que mencionas, si es cierto, aquí no lo sé, no lo sé. Digo, hay muchas cosas que pensar, pero todavía no lo sé.
Gracias.
Bueno, estamos sobre tiempo, le agradecemos a Valente. Nuestra siguiente charla es en 5 minutos. Yo creo que la misma función.
Yo creo que sí, a menos de que la quieras usar.
Más estamos donde puedas cargar porque solo tiene 37%.
Ah, ok.
El lápiz sí está en 100%.
So our next speaker is Ana Belén Áviles. She will continue talk about the frame of the reals and real value functions and other maps.
Okay, thank you. Liz, ¿puedo quitarle el sonido aquí? Que se oye mi voz del son. Ah, bueno, sí nos da igual, no importa. Ah, ok, ya, perfecto. Ujú, perfecto, gracias. Sí. Ok. ¿Es este?
Puedes calcular el espectro. Sí.
Ok, gracias. Okay, sorry, thank you. So maybe we should go, just want to recall a few things that we mentioned yesterday. So remember this talk is about sublocales, frames, and then we were gonna give, wait. Yes, we were gonna give first some general background. Then we were going to discuss the frame of reals. And lastly, which will be today's topic, talk about some insertion theorems. Okay, so just to remind everyone what we talked about yesterday is, so we defined a category of frames and locales, and we saw the adjunction between topological spaces and frames, where we take the opens, and here we take the points. Then we defined what a sublocale is, a sublocale S of L, and we consider the whole class of sublocales, order by inclusion. We have arbitrary intersections. We have joins. The void sublocale is the sublocale which is the top element, and we have the top element of this lattice is the whole L, right? Turns out that this thing is actually a coframe. That means that the lattice with the opposite order is a frame. We saw two different kinds of sublocales, which are OA, which are the opens, and the CAs, which are the closed. The closed play an important role because if we take the lattice of all the closed sublocales, ordered by the opposite order, this is a frame, and it is isomorphic to L. And we have the canonical map that goes from L, this is an isomorphism, to SL up, where every element goes to its closed, right? And this is included in the whole frame of sublocales, right? I think from the general background, this is it. If anyone has a question or wants me to remind anything else, let me know. Okay. Then we looked into the frame of reals. So I told you that we could always take the lattice of opens of the real line. This is a frame, but we can actually build the reals as a frame built on generators presented by generators and relations. So the generators are all the elements of this form, P dash, dash Q, for P and Q rationals, right? So you can think of those as intervals from P to infinity and minus infinity to Q. So of course the relations, I won't mention them again, but the relations are the relations that the intervals are expected to satisfy. Or Dedekind cuts, you might think of it like that too. Yeah, so we said that a continuous real valued function on a frame L is a frame homomorphism from the frame of reals to L. Okay, we gave a little bit more intuition, but I don't have time to go again through that. And then we said, okay, what if we want to give like something that's not continuous? So we defined a general real valued function on L, and we said it was a frame homomorphism from the frame of reals to the frame of sublocales, right? So the lattice of generalized subspaces. So like the power set, but it's not. F, right? And we said that F is lower semi-continuous if, wait a minute, give me 1 second. Yes, if this, I always get them confused, the right and the left, so that's why. If these ones are closed sublocales for every R in Q, it's upper semi-continuous if these ones are closed for every rational, and F is continuous if both of them are closed, right? For every R in Q, right? And then we saw that because we have the isomorphism between the closed sublocales and L, this notion of continuity actually is the same as this notion of continuity, right? So there's no problem with our definitions. And I will usually want to think on general real valued functions and then check if they are continuous, right? We gave 2 examples of real valued functions. So I showed you how can you define the constant. So for P, a rational, we define the constant real valued function, right? So it is continuous. And I told you it was defined like this, right? And if we take the other ones, then we have L or 0. If R is less of Q. So the way to define them, if you would ever like to define a real valued function, what you have to think is, think of preimages, and you're defining a function through preimages. Instead of saying this point goes here, you're thinking of, okay, what are the preimages of the closed? And then that should give me the way to define it in frames. Then I also told you could define the characteristic function of a sublocale. So if you have a sublocale S, I can only define it if it's complemented, right? And it's defined like this. I won't write it all over again. like this with some conditions here, or, and I didn't even put here, the image of this generator and the image of this generator. This one goes to L, S, or 0. You just have to check like if R is bigger or equal than 0 or bigger or equal than 1, whatever. You have to just work that out. And I told you that S is not necessarily continuous, right? Because to be continuous, we need that all the images to be closed sublocales. So with L and the void sublocale, we have no problem. They're trivially closed. But S and the complement, pseudo complement of S are not necessarily closed, right? So you would want S to be closed and its complement to be closed. So you want S to be closed and open, right? So for the characteristic function to be continuous, you need to have S is open, right? So it's a closed and an open sublocale. Okay. About the real functions, I just want to mention something right now. So in classical topology, we care about how to separate 2 points, right? With open sets. But then you have some separation axioms that, okay, now I can separate 2 points, but now I want to separate 2 closed sets. And you use opens to separate closed sets. But then you also use real functions to separate sets or points, right? So yes, if you have 2 sublocales, S and T, you say, okay, it might be a good idea to start with the topological definition. So if you have a space and you have A and B, 2 subsets of X, you say A and B are completely separated if there is a continuous function from X to the reals such that A is contained in the preimage of 0 and B is contained in the preimage of 1, right? You can take here the interval, or you can actually make F to be bounded, right? So what you do in frames is if you have a frame L and take S and T sublocales of L, we say that S and T are completely separated if there is a continuous real valued function that is a frame homomorphism from the frame of reals to SL up, but it has to be continuous, such that S is contained in the image of these, and T is contained in the image of 1, right? Because, let me choose another, here. Yeah, this is as saying, if it's bounded, this is the same as saying that A is contained in the preimage of these closed, right? And this is the same as saying that B is contained in the preimage of this one, right? Because it's bounded. So this is exactly how I'm translating it to frames, right? Maybe here I could also ask for F to be between 0 and 1, right? And then I very easily have this is precisely this, and this is exactly this one, right? This thing should be read as the preimage of this interval. and this as the preimage of this one, right? So basically, two sublocales are completely separated if I can separate them with a real valued function. Okay, so now let me start with part 3. So I want to talk about insertion theorems. And now everything that I've told you so far will be useful and will come together. So yeah, let me just follow my notes, because if not, I start saying things. Okay, any questions so far? Okay, so what is an insertion theorem? So an insertion theorem is usually something like this. So you have this, I'm going to do it first topologically, right? Classically. So if you have two functions, and usually these are some kind of general functions, they're not continuous or anything, you will have that these two conditions will be equivalent. These are the kind of insertion theorems you want. You have two functions and you have g less or equal than f, right? So what it's telling you, it's giving you conditions, equivalent conditions to put a function in the middle. So it's telling you, okay, there exists an h from x to r, and usually it will be continuous, or you want it to have a stronger property than this too, such that it is in between the two of them, right? And having the existence should be equivalent to some condition, right? We will see some examples and you'll get a better taste of it. So this would be an insertion theorem, and it usually implies two other kinds of theorems as corollaries, where you have a separation result, which tells you if A and B are subsets of X and they have some kind of property, then A and B can be separated by a real valued function. Right? And you have usually an extension theorem. These are the kind of results that if you have a subset of a space and you have a function that goes from A to the reals, then you can actually extend it from the whole to the whole space, right? Which means that if you restrict the big one, you obtain F, right? So the insertion theorem usually gives you a separation result and an extension result, okay? So let me give you some examples that I'm sure all of you already know. I will do the topological, I will tell you about the topological result first, and then I'll go to frames, okay? Because there has been a lot of papers about insertion theorems in frames. And yeah, okay. So yeah, I'm going to talk about 3 insertion results. The first one is for normal spaces, right? The second one is a general insertion theorem. And the third one is for uniform spaces. Okay, so the one for normality, I'm sure all of you already know it. So remember that a normal space, right, is a space, let's do a drawing, we don't need to go through the formal definition. If you have two closed, F1 and F2, you can separate them with 2 disjoint opens. That's normality. And okay, so let me tell you what's a normal frame. So a normal frame would be, okay, so if I have 2 closed sublocales that are disjoint, CA and CB, then there exist X and Y, 2 opens that are disjoint, right? And that contain, so that CA is contained in one of the opens and CB is contained on the other open, right? Because of how the closed and the opens preserve meets and joints, you can actually define normality in a first order way. So if A join B, this is equivalent to saying that if A join B is equal to 1, there exist X and Y such that X meet Y is 0 and A join X is equal to 1. This is equal to B join Y, right? I kind of used all the properties of the meet of closed is the close of the joins and all of that we saw yesterday. Okay, so this is a normal frame or a normal locale. Okay, so the insertion theorem about normal frames, normal spaces, says the following. A space X is normal if and only if for every pair of functions f and g from x to the reals such that g is less or equal than f and f is, I think, lower semi-continuous and g is upper semi-continuous, then there exists an h from x to r continuous in between. Right? So space is normal if and only if I have two semi-continuous functions, I can put a continuous function in between. And this translates very nicely to locales. So let's just do this. A locale or frame L is normal. We already know what normal is. If and only if for every pair of functions, but now they will go from the frame of reals to SL up. Again, where G is less or equal than F. F is lower semi-continuous. G is upper semi-continuous. And there exists an H, again, from the frame of reals to SL up. That is continuous, that sits in between, right? So you have exactly the same result. The proofs are not the same, but they're kind of similar. Okay, but then we have the famous corollaries, which I know maybe the insertion theorem you didn't know, but at least you know Urisan separation lemma. So these results come as a corollary from the insertion theorem, right? So if you apply the insertion theorem to two characteristic functions, you will obtain the separation lemma, right? So what does it say, Urisan separation lemma? Let A and B be disjoint, closed sets of a space X of closed sets of a normal space X, then there exists a continuous function such that such that the preimage of 0 contains A and the preimage of 1 contains B. So as I told you before, this means that A and B are completely separated, right? So it tells you if you have two disjoint closed sets, you can separate them with a function. That's horizon separation lemma in spaces. Actually, it's an if and only if. The space is normal if and only if you can separate closed sets with a real valued, continuous real valued function. And you have the same result in locales. You have that if S and T are disjoint closed sublocales of a normal locale or frame L, then there exists a continuous function, but now you have to change that direction from the frame of reals to SL up, such that S is contained in here and T is contained here. Right? So it works very nicely. I wish I could go through the proofs of this, but they get a little technical and I don't think it's worth it. The way to prove it is if you already have the insertion theorem, what you do is if you have two closed sublocales, closed of A and closed of B, what you want to do is you take the characteristic function of C of A and the characteristic function of the open of B. These are not continuous, but one of them is lower semi-continuous and the other one is upper semi-continuous. So by the insertion theorem, you will find a function here, H, and this H is the one that will separate you this closed with this closed. Very nice proof, actually. And of course, so that insertion lemma gave us this separation lemma, but we also have the extension result, which is Tietze extension theorem, which says a space is normal if and only if every closed subset is C star embedded. Okay, I wrote it like this, but let me explain. What is it to be C star embedded? It just means that we can extend functions, right? So a subset A of X is C star embedded if whenever I have a bounded continuous function A to the reals, bounded and continuous, then I can extend it to the whole space. And the restriction to A is just F, right? So a space is normal if every closed sublocal is, if every closed subset can is C star embedded, which means I can extend functions. So in the reals, if you have a closed interval and you have a function here defined here, you can always extend it. But for instance, if you have an open, let's say kind of like the tangent here, this one is not C star, right? You cannot extend it to the whole real line, okay? Those are easy examples. Yes, okay. So we have the same for frames. So if you have a locale L, it is normal if every closed sublocale is C star embedded. Now, what does C star embedded means? It also means that you can extend functions. So let's write the definition. So as a sublocale of L is C star embedded if whenever I have a continuous bounded function, sorry, here F has to be, bounded and continuous. Here too, my F has to be, F is up, right? Because it goes, it's a function, real valued function on S. That's why I have the S here. If I have a function here, I can extend it to a function like this, SL up. So if this one is bounded and continuous, I can extend it to something like this. Here, what map do you have? And I will show you one. So if S is a sublocal of L, you have the D embedding, let's call it J, is a localic map, right? And then you'll take, as I told you yesterday, if you have a localic map, you can take the pre-image. So you have SL up to SL, no, SS up. You have the pre-image here, right? This is the frame homomorphism. So this map is the one you have here, right? So being C star embedded means that for every F, there exists an extension such that this diagram commutes. Now, this pre-image looks very messy, but in fact, it's not. It's very nice. It's if you have a sublocal of T, how do you get the sublocal of S? You just intersect with S. So, yes. So you obtain TC extension theorem for locales, right? A locale is normal if and only if every closed is C star. Okay. Okay, so this is the insertion theorem for normal spaces and normal locales. Yes?
The above diagram, the extension diagram is in frame, right?
Yeah, this is in frame.
And it's for any sublocal, S is closed or open or any?
So you define C star if this always happens for any function F, but it's very, in normal spaces, this happens for every closed, but it doesn't happen for every open.
In topological spaces is for closed.
Yes, in locales too. This only happens for closed. Yes. But for instance, if you have, for example, extremal disconnected spaces, this happens for every open. So it depends on which kind of frame you are, which kind of sublocales will be C star. C star means they can extend the function to the whole space. Okay, so there's a more general insertion result, which is Blair and Lane insertion theorem, which tells you if you have two functions, f and g, from a topological space to the reals, such that g is less or equal than f, it gives you these equivalent conditions. The following are equivalent. 1, there exists a continuous function in between, h, right? H from x to r continuous. So f, g and f are general functions, h is continuous, if and only if these two, I wrote it already in locales, sorry. Let me just, if this and if these two sets, these are pre-images, sorry, are completely separated for every r less than s, right? So it's telling you if you have two functions, it's giving you the equivalent condition to have a continuous function in between. This is a very useful theorem. And you also have it for frames, right? So again, if you have two continuous functions, two general real valued functions, sorry, this should be SL up, then you can give one in between, right? But it looks like this, that it's continuous if these, but now these two subsets will be GS and FR if they are completely separated for every R less than S, right? And yes, this is a very useful theorem. As a corollary, I would just like to mention the extension result. And maybe in this one, I will like to sketch both proofs in the topological spaces and in locales so that you see how different they are. And even if I'm showing you like, oh, this just goes directly, proofs don't translate that well because you don't have points, and topologists love points, and they say, okay, f of x is this. You cannot do this in point 3, right? So the extension result tells you if, yes, it says it's Urizen extension result. Well, there's another version of this, but because depends how you phrase it. There's Urizen and there's also Moravka extension result, but I will phrase it Urizen way. So S is C star embedded. That means that I can extend all functions of S to the whole space if and only if A and B, if A and B are subsets of S, if they are completely separated in S, that means I have a continuous function on S that separates them, then they are completely separated in the whole space, right? In the whole X. That means that if I can separate them in S, I can extend the function and I separate them in the whole space. You can do this in locales too. So S is a sublocale, A and B are sublocales, right? And they are completely separated in S, then they are completely separated in L, right? So let me more or less tell you, and I will go through the details because I don't even like this proof. So I don't even know, couldn't do it right away. But in what happens in spaces. So in spaces, so the hard thing to prove, this way is easy. This way is the hard one, right? Because from a function, you have to build the bigger function. So you want to show for S to BC star, given a function like this, f, you want to build one that goes from X to R, right? So just to tell you how it goes, I really hate it. It has to be bounded, right? So it means that the function, there's an M that bounds it. Then you consider this bounds, and then you build two families of functions, and then you take the sum of all the GNs, then you bound the sums with these Rn's, and you see that this series has a limit, so then this one converges, and then that convergent is the one you want. I hate this proof. It's very complicated. How do you do it here? Here, well, it's not, okay, I won't lie to you. It's prettier, but it's not like super easy, okay? But so you start with a function like this, right? And then you give two families of sublocales. The first family, you do like this, you take yes, you take the closed sublocales of this form and L, right? Here, zest of 0. You take these family. Oh. And then you take these other family. Instead of taking, you take the complement of the closure and the same, right? So you take these two families. These two families will generate you two functions, f1 and f2. You use this insertion theorem, and the function you obtain in between is the one you are looking for. So I think it's a very beautiful proof. It's still technical, but at least you don't have to do infinite series. Okay, so lastly, I would like to mention the uniform insertion theorem. I will write the theorem, but then I'll have to introduce a lot of theory again because we don't know what a uniform frame is. So I will do a bit of theory and then I will arrive to the point-free version of the result, okay? So this insertion theorem for uniform spaces, was due to Price and Vilimovsky. And it says the following. So X is a uniform space, right? And if I have two functions, f and g, from X to the reals, general, they don't have to be of any kind, just functions, such that f is bigger than g. The following are equivalent. One, there is a uniformly continuous function h from X to R such that it sits in between. And the equivalent condition for every positive delta, there is a uniform cover U of X such that for all natural numbers, this set and this one are STNU far. The star, this is the star operator where you, okay, we'll go through that. Whenever S minus R, this happens. So it's not a very nice condition, but you will see, you can see why if you want something to be uniform, you need this kind of condition. So yeah. So to even enunciate this theorem, we need to know, so we want this in frames, right? We don't know what a uniform frame is. We don't know what uniform continuity is. We don't know what a uniform cover is. We don't know what does this mean, okay? So I'll give you a crash course in uniform frames to be able to enunciate this theorem. So then let's go back and define this. So what's the problem with uniform frames? So classically, you have a set, right? And then to the set, you define a uniformity. And this uniformity gives you a topology. The problem in frames, and when you try to define this, is that if you have a frame is like a topology. You already have a structure. You cannot start from zero. You cannot start from a set and then define a uniformity on the set, and then you can't. So this is how uniformities are defined. I will tell you how they do it in order to solve this problem. Because what you do is actually you say if a frame is compatible with uniformity or not. You don't define a uniformity on the frame. You just say if the frame admits a uniformity. Okay, and the easiest way for me to define uniformities is with covers. I don't like entourages and those things. So I will do it the cover way. So a subset U of a frame L is a cover if the join is equal to the top, right? So it covers the frame. We can define an order in the covers. So U refines V if for every U in U, there exists a V in V such that U is less or equal than V, right? And we can define a star operator. So U a cover, A an element in the frame L. We define U star A as the join of all the U's such that U meet A is different from 0, right? This is just saying if you have, let's think in spaces for a minute, if you have an open set, you're taking all the elements of the cover, all the open elements of the cover that touch your set, that cover your set, right? So you would have that A is less or equal than UA. You have other properties. You also have, I didn't mention this, so I will avoid it, but, no, sorry. You have UA, sorry, we have defined UA. So now we can define the star between two covers. This is just, you take all the U star A for every A in V, right? And you will have that for a cover U refines its product, right? So you have a cover and you're making it kind of bigger. You also have this other nice property. So you have that the star view in a join of elements is the same as the join of all the stars, right? I won't go into this, but this means that this star operator, if we call this an operator, preserves arbitrary joins in frames. It means it has an adjoint. And then you could look at the adjoint and play with it. This is just a comment. I won't do that. But then, okay, so you defined U star V and you can take it for one, so you can actually define it recursively. So U1 is U. Okay, U2 we say is U star U. UN plus 1 is just U to the N, okay? Notice that this operation is not associative, so it's really important that I'm doing it on the left. Okay, so this is basically the star operators and the covers. So what is a uniformity? So let L be a frame. A uniformity U is a family of covers that behave nicely, basically. So U1 and U2 tell you they have to be a filter. So if U refines V for some U in U, then V has to be in the uniformity. If U and V are in U, then the meet, I'll tell you what this is, has to be in U. This is just U meet V, where U is in U and V is in V, right? This is again a cover. So you basically want your family, your uniformity, your family of covers to be a filter. Then this one is the most interesting property. If U is in your uniformity, you want the existence of another cover in U such that its star refines U. And so if you look at the definition in topological spaces, you can very easily deduce all these three properties. But the last property is just for frames. U4, which is the admissibility condition, tells you that for every element in L, each element has to be the join of all the B's in L such that B is uniformly below A. What does this mean? This means that there exists a cover in U such that U star B is less or equal than A, right? This is called the admissibility condition because this condition, what it's telling you is that the frame admits the uniformity. And this is how you're doing it. Because you cannot start from a set and build the uniform frame because you don't have points, you have a frame, you have a topology, you have a uniformity, and you check if it's compatible with the topology. This is what that condition does, right? So if you have a pair LU, this is called a uniform frame, right? In fact, and for the stuff that we'll be working, we don't need this whole thing. We can work only with pre-uniform frames, which only require the first three. So this is perfect, right? Because almost every frame has a pre-uniformity, but not every frame admits uniformity. So you have these three. You can take, instead of taking the whole uniformity or the whole pre-uniformity, you can take just a basis. So you take, this will be a basis of a uniformity. This would be a basis of a pre-uniformity. So if you have a basis, what you do is you take, since this is just taking all the covers that are above, if you have a basis, then you just take all the ones that are above. So, yeah. And yes, so if you have two frames with a uniformity, pre-uniformity or pre-uniformity, a frame homomorphism H is uniformly continuous if the image of every U is in V, or every U in U, right? Now, if you have bases, which is usually what you do, you just say H of U is refined by some V such that B is in B, right? So for every U in U, B refines the image for some V in B. This automatically tells you that this is in the uniformity. Yeah. Okay. And you have the category of uniform frames and pre-uniform frames, right? With uniform maps and uniformities and pre-uniformities. Okay, so let's give an example. And so the frame that we already know very well is the frame of reals. So take the frame of reals, and we're going to give it the usual uniformity, right? The one that we work with. So take dn. So dn is defined as all the elements Rs in the frame of reals. So I think I didn't tell you this. Let me just do a little note here. Rs is just the meet between these two elements, right? So if you have the two intervals that go like this, then you obtain the bounded interval. Okay, so I take all the intervals of this kind, intervals, such that the distance between them is 1 over n. This is a cover, right? I take all the intervals of a certain length, I cover the whole space. You can actually do this this is for every n natural number. You can actually do this for every positive rational, right? So if you take all the family, let's call it D, of all D deltas, this is a base for a uniformity. For a uniformity in the frame of reals. And it's the usual uniformity given by the usual topology in the reals, right? So these pair, no. The frame of reals with this uniformity is the one we're working with, right? The usual uniformity. So we've worked, so I already defined what uniform continuous maps are. So, and continuous real valued functions. So what would be a uniformly continuous real valued function? So if I have a frame L, U a pre-uniformity. If I have a frame homomorphism from here to here, and now I usually, when I write the maps, I won't write the whole pair, but from now on, I'm referring to uniform stuff. So I have the usual uniformity and the uniformity in L, or pre-uniformity. So a frame homomorphism of this kind H, by definition, it's continuous. To be uniformly continuous, by the definition I gave before of uniform continuity, this would mean that for every positive rational or natural number, there exists a cover U in the uniformity of L, such that U refines the image of the delta, right? The delta, remember, so this would be, let's write in, the image of all the intervals where the length is 1 over delta, right? So there's a cover in the frame L that refines the image of the cover of the reals. Yes, okay. Let me see, where are we so far? Okay, yes. There's still okay, so we have, this is the general context. We have uniform frames. I gave you already the standard example of uniform frame, which is the reals with its usual uniformity. It can be extended, everything, right? Because here, when I'm defining, so this would be, this would be a uniformly continuous real valued function on L, right? So I'm defining uniformity, but I'm assuming continuity. This doesn't happen in classical topology. In classical topology, it's the other way around. You define uniform continuity, and that implies continuity. So I want a general real valued function, define uniform continuity, and obtain continuity from that. Here, I'm doing it the other way around. So I want to take it to another level. So that's what I'm going to do now. Okay? So I'm going to go to I did everything for the frame. I'm going to take things to the frame of sublocales, kind of. So let me hit this. Okay. So yes. If I have a cover, yes, if I have a cover, if U is a cover of L, then I can take OU, right? This would be all the opens where U is in U, right? So if U is a cover of L, that means that the join of U is equal to 1. If and only if the open, right, is equal to L, but this is just the join of all the opens, right? So U is a cover of L if and only if I take the open covers. The open cover is a cover of SL, right? Of the sublocales. So the join of all the opens gives me the whole space. So instead of thinking of a cover in L, for every time I see a cover in L, I'm actually thinking of all the open sublocales, right? Which form a cover too. Okay. And we say the following. I can define the star too. So, okay, let me define something first. If I have S and T, two sublocales of L, we say S and T are U far if whenever S, if for every U in U, this is a cover, U is a cover of L. Let me put this here. U is a cover of L. If whenever S, I say S and T are U far, are U far, if for every element in the cover, if S intersects with the open element, right, then it cannot intersect T. Right? I don't know if this makes sense. I think it's very intuitive. So if you have a space, you have two sets, S and T, and you have an open cover. You say these two sets are far, are U far, if whenever a U intersects S, then it cannot touch T, right? So that is to say, you cannot have kind of this situation, right? This would be that S and T are not U far. Okay, so this is a nice notion, and we actually needed it for the insertion theorem. Yeah, and I also need this other thing. Do I? I don't think so. Well, so the relation of farness, of U farness between sublocales behaves very nicely. So you could think of it, and so you know that we have the two sublocales are completely separated. Well, two sublocales being U far is kind of like the analog of complete separation in the uniform context. And this is not just intuition, this is what it is. So, yeah, so we have the far, we've defined what U far is, we defined the open covers. So let's define a general definition of uniform continuity. So we had, okay, so we say F, a frame homomorphism from the frame of reals to SL up, that is F, a general real valued function on L. We say this is uniformly continuous if for every positive rational there exists a cover U in U. Remember, I'm always in the context where L has a pre-uniformity or uniformity. There is a cover here such that if I take the open cover, this is a cover here. This one refines this. In D delta, right? It's a natural way to translate it. Remember that the original definition that we had was, okay, this is uniformly continuous if you have this, and for every delta here, there exists a U here such that U refines this. right? But here we assume continuity. Here we're not assuming continuity. So this is a more general definition. What's interesting is this definition works very nicely, and you can actually show that if a function f like this is uniformly continuous, well, then it is continuous. Which is what happens in the general context. Something uniform continuity implies continuity. Okay? And again, to prove that this, if it's continuous, you want to make sure that this function is of this kind. You remember, you always have to use the isomorphism between these two frames, right? Yeah, okay. So I think we're ready to enunciate then the uniform theorem. I would like to mention, though, in order to prove that insertion theorem, we first showed a weaker version. So we showed that if LU is a pre-uniform frame, and I have a general real-valued function, f, we prove these two conditions are equivalent. F is uniformly continuous in the sense I just said, if and only if these two sublocales are U far whenever S minus R is bigger than 1 over delta. These are equivalent conditions. Right. This would be a corollary of the insertion theorem, but we actually proved it first, and that helped us prove the bigger theorem. Because the big theorem says this: LU be a pre-uniform frame. And we have two general real-valued functions from the frame of reals to SL up, right? Then the following are equivalent. One, there exists a uniformly continuous function, H, from the frame of reals to SL up, in between G, H, and F. Okay, here I forgot to say G is less or equal than F. So there is a continuous, uniformly continuous function in between, if and only if this condition happens. For every positive rational, there exists a cover in the pre-uniformity such that for every natural number, these two sublocales are UN bar whenever S minus R is bigger than N over delta, right? So the condition is very complicated and you cannot get rid of this, right? The only way to get rid of it is if you actually have, instead of have two general, you have two general, but you ask them to be bounded. If they are bounded, you can give a uniformly continuous function in between, and you can get rid of this. Here you would just have a 1, which makes the condition way nicer, right? But then, as I told you before, if we apply this insertion theorem with two different kind of functions, we will obtain a separation result and an extension result. So the separation result, let's call it separation theorem, tells you the following. LU, a pre-uniform frame, S and T sublocales of L. You have S and T are U far for some u in the pre-uniformity if and only if there is a uniformly continuous function h from the reals to SL up, such that it separates them, right? So T is contained in the preimage of 0, and S is contained in the preimage of 1. You can make it bounded, right? How do you prove this? You apply the insertion theorem for the characteristic functions, the closure of S and the complement of the closure of T, right? Yeah. So if you apply the insertion result for these two characteristic functions, you will obtain the uniformly continuous function that separates the two sets. And there's another, the extension theorem that you obtain is LU, a pre-uniform frame, S, a sublocal of L, right? Every bounded uniformly continuous function f from the frame of reals to S up, right, can be extended to a uniformly continuous bounded f to the whole L, right? And again, you will have that the diagram that I showed you before commute. I omitted something here, but this is a uniformly continuous function on S. You have to give a uniformity in S, but it's the one inherited from L. So everything works nicely. How do you prove this theorem? You prove using the insertion theorem. You give two special functions. So intuitively, this is what you do. Imagine this is S, this part of it, right? And you have whatever function, I don't know. Well, this is not uniform, but it doesn't matter. You're going to give a G, which takes 0 outside of S, then the function in S, and then 0. And you will take F to be 1 outside of S, the same function in S, and then 1 outside of S. And then the insertion theorem will give you the uniform function in between. Yeah, and so in the last, I had planned to have more time, but I don't. So I just want to tell you that this insertion result in uniform frames looks very specific, but you can actually apply it and obtain the other insertion results. So for instance, for any frame L, you can give it a uniformity, let's call it UR. Sorry, this is a pre-uniformity, right? This pre-uniformity, so for every frame, you can give it a pre-uniformity given by functions of the reals and the covers. So you will take all the covers U of L such that U is refined by this cover, by these kind of covers. FK, right? Where every Fi is a function, a continuous function, right? And the Dn were the sets, the covers of intervals, right? So remember, Dn were the intervals that had one fixed length, right? So you're taking the covers of the reals. Remember that this gave the uniformity in the reals. You're taking the images under continuous functions, and this will define you a pre-uniformity on a frame L. This pre-uniformity, and let me just mention it, I won't go into details. This is a uniformity if and only if L is completely regular. Okay? But anyways, even if you just have the pre-uniformity, with that pre-uniformity, this insertion theorem, right? This insertion theorem is this one. Well, I have to go way back. It's this insertion theorem. Because with that pre-uniformity, uniformly continuous function are continuous functions. And the farness, the U farness is actually complete separation. Yeah, and you can see that being far with that pre-uniformity is actually just being completely separated. So it's a general theorem. It gets a little messy, but all the theory developed in uniform frames to get to this theorem. I think it's actually nicer more than the theorem itself. But it's nice that you can apply it for every frame. And yeah, any questions? Sorry, I didn't stop in the middle because but I thought I was not going to reach the end. Yes.
When you have a pre-uniformity in a frame, how do you define the uniformly continuous? I don't get what happened is if the frame don't admit a uniformity anyway you have continuity uniformly.
Yeah, so we call it uniform continuity, even if you have a pre-uniformity. It's just the name. You could call it pre-uniform continuity, but it's the same kind of morphisms. But in one case, you might have uniformities or you might have pre-uniformities.
Okay.
Yes.
Thank you.
This theorem was originally thought to be, we thought we were only going to be able to prove it in uniform. We thought we would only need, the admissibility condition was going to be very important, but we never used it. So it's true for pre-uniform frames, which is actually very good because it allows you to do it for a lot of frames. Yes. I don't know if that answers your question. Okay, sure. If not, we can talk later. Yes.
Is there any other questions?
Very nice workshop. Very interesting. First, you have already mentioned that you can give an operation in this LR that you were not interested to talk a lot about that. Just a question, if you know, does it define a quantal? Like the operation, whatever it is distributive with the supremum?
You mean in the frame of reals?
Yeah.
Because every frame is a quantal.
It's already a quantal.
Yes, every frame is a quantal.
But it has, yeah, but it's a quantal with the MIT.
Okay.
No. You say that you have an extra operation, like an addition or product in these functions. So if the supremum distributes with these different operation.
But you're taking the operation of the functions or in elements of the frame?
I thought those were defined as functions. What were the elements of this
You,
LR.
yeah, ajá.
Es que, pero el anillo es entre las operaciones, entre ellas mismas, ¿no? Entonces, cuantales, tienes una operación, tienes un orden y tienes una operación y si es distributivo con el orden. En LR, ¿no? Eran funciones, ¿no?
Ah, ok, ya te entendí. LR, es que LR los reales. Y si te tomas RL, sí, este es el anillo.
Y funciona pero tienen un orden, ¿no?
Sí, tienes un orden, tienes una suma,
Eso.
tienes un producto,
Y es
tienes...
distributivo, bueno, tiene esa propiedad cuantal, sea con el producto, sea con
Creo
la
que
suma.
sí,
Perfecto.
creo que sí.
Gracias.
Ujú.
Esa era una.
Sí, eso es porque es arquimidiano. Ujú.
Digo, no sé bien qué es eso, pero las propiedades que buscan se parecen mucho a eso, ¿no?
Ujú.
Y la otra, la pregunta de oro. Las preuniformidades ¿esta categoría es una categoría topológica?
No lo sé.
Sí, ok. ¿Podrías mostrar la definición a través de preuniformidad, por favor?
Sí, es esta. Es U1, U2 y U3. Es un marco con una familia de cubiertas y cada cubierta, la familia cumple que es un filtro y está, a mí me gusta como una cerradura aquí.
Ok. Estaría súper saber eso.
Eso es BD, ¿verdad? D por D.
Sí, sí.
Y por último, fuentes para leer sobre estos espacios estos marcos de preuniformidad.
Bueno, en el libro de Picado creo que lo menciona.
El primero,
El primero.
Ajá.
También hay unos artículos, creo que es una serie de 3 artículos de Alex Poulter que se llama Uniformities, creo que one y el Uniformities two o algo así. Y creo que en el 2 llega a marcos métricos, no lo sé. No me acuerdo si es este o es otro. Y luego está la tesis de Picado, su tesis de doctorado. Ahí introduce la categoría de marcos uniformes y hace la comparación con entourages y cubiertas. Y gogues o no sé cómo le llaman. Ujú. Pseudométricas, básicamente.
Padrísimo.
Ujú.
Pues ha hecho bastante. Qué raro que no se haya contestado. Sí, sí. Ok.
Sí.
Muchas felicidades, me encantó.
Gracias.
Padrísimo.
¿Más preguntas? ¿Mencionaste que el puntito este no era asociativo?
No, no, sí, o sea, esto, digámosle así, no es lo mismo que hacer esto. Ujú, ujú.
Pero conmutativos sí. O sea, no importa por dónde lo multiplicas, ¿no?
No, creo que sí afecta.
Sí.
Sí, sí. Ujú.
Otros.
If there are no questions, I will just want to say thank you very much for giving me the opportunity to talk about the stuff that I like here. Thank you, Angel, for inviting me. Thank you for all the organizers. It has been a while that I was not in Mexico giving a talk, so I'm very happy to be back. Thank you.
Ahorita ya está el coffee break y creo que va a haber una flash talk, ¿no? Una plática rápida. Our next speaker is Bernardo Villarreal Herrera from CIMAT Mérida. He's going to talk about the frame smashing localizations and the Ziegler spectrum.
Okay, thank you. Thank you for the invitation. And just a disclaimer, I'm going to talk about a topic that I'm not really an expert, and really the experts are Angel and Juan Omar over here. So any deep question, you can forward it to them. So, okay, so here it goes. Okay, so we already saw with Juan Omar how to, well, how we can associate to a category under some extra hypothesis, a spectrum, right? And to me, the best way to think about this Balmer spectrum is like with two particular examples that I have in mind. So the first one is the Zariski spectrum of a ring, right? This is pure a space that we get by purely algebraic properties of the ring, right? And thank you. No. Okay. And the next one for me as an algebraic topologist is homology of spaces. And one of the axioms in a homology theory comes from the long exact sequence associated to a pair, or in this case, you can think of a map. And the reason that actually exists is because we have this sequence of spaces that I think Juan Omar draw a bit of it. You sort of have a space X, and you can, so everything in algebraic topology is up to homotopy. So you can just deform things, and then you can put this into something that is called the mapping cylinder, right? Which has that homotopy of your space Y, which is really this. And then you form the cone, which is just collapsing this top cap of the cylinder. And then you collapse the whole thing, right? So this is the cone of the map to get suspension if you just collapse the whole thing. Like if you have a cone and you just collapse the lower bottom, you get a suspension. So this is the suspension of the original space, and then you can continue this construction that is well defined up to homotopy. And because of this, this is like this is actually an exact sequence in homotopy, and then here's the extra ingredient that we have in when we do homology is that we have this sequence, and really comes from this distinguished triangles that Juan Omar mentioned before. And up to homotopy, we can, well, not up to homotopy, so we can promote spaces to something called spectra. And I won't get into what a spectrum is, but if you know a bit about homotopy theory, a cohomology theory, like singular cohomology or, well, algebraic K theory, sorry, real K theory, they all come from a spectrum. So spectrums are like cohomology theories. And I'm gonna denote this category as SH. So it's called the homotopic category of spectra. So we take spectra and we take things up to homotopy. And in there, we also have this kind of sequences. There are distinguished triangles, and then we have all the other axioms that Juan Omar told us about triangulated category. Okay, so these are like my two main things that I have in mind to sort of go around whatever the Balmer spectrum is. So I'm going to associate to a category that has the structure of a triangular category, something that resembles the Zariski prime spectrum. That's going to be the Balmer spectrum, but I need this extra structure. There is the symmetric monoidal tensor product, so that I can talk about ideals, right, in our category. Okay, with Juan Omar, we were only seeing the case of, how do you call it, essentially small category. So that means that the class of isomorphisms of objects is a set. And in general, we don't, I mean, this is a bit restrictive. So we want to work with bigger categories. But we also need a notion of what sits inside that big category that resembles the essentially small category that we can associate to it a Balmer spectrum. So a compact object in a category, it's the one that after taking, if I take hums of a coproduct of objects in X in the category T, sorry, I can basically, if hum commutes with the hum with source C commutes with coproducts. And I'm gonna consider categories that are generated in some sense by the compact objects. So generated as coproducts of these smaller objects. So just think of compact objects as small objects in your category. And we already saw what rigid is with respect to the tensor product. And this is what, like the basic object that I will be considering, and we call this big TT category. Okay, so there's a lot of stuff going on here. There's a lot of extra definitions here, but for the moment, just think you have a triangulated category with a tensor product, and that it has a subcategory of compact objects. In the examples that Juan Omar told us, like the derived category of a ring, for example, the compact objects are the perfect, the perfect complexes, right? And well, in homotopy theory, the compact objects are the spectrums that are finite in some sense. Okay, so what I was saying is that the full subcategory of compact objects is essentially small. So to it, I can associate the Balmer spectrum, just as Juan Omar told us. And these are the underlying set of this space is it's missing a prime there. It's prime tensor ideals. Sorry. And and the example I started with was the Zariski spectrum of a ring. So it somehow generalizes the Zariski spectrum. And because if I take the derived category of a commutative ring and I associate with the Balmer spectrum of its compact full subcategory, sorry, its full subcategory of compact objects, I get again the Zariski spectrum of a ring. So you can think of it of a bit going away from well, sort of, it's very closely related to commutative algebra, but at the same time, it includes so much more. And that is a particular example of the category, of the homotopic category of spectra. So, I mean, you know, the Zariski spectrum is like the building blocks of algebraic geometry. Like for a scheme, you have a scheme. If locally is the Zariski spectrum of a ring, and well, you might think that the Balmer spectrum, well, if you have this kind of relation for the derived category of a ring, then maybe you always get a scheme. So you're really not going away from algebraic geometry. But the point is that you do. This, I think, something that actually Balmer showed, that the Balmer spectrum associated to the category, homotopic category of spectra is not a scheme. And I plan to draw what the spectrum looks like. And this is from a classical result of Hopkins and Smith. And this actually has a nice drawing. So I'm going to draw the points, so the prime ideals of this spectrum. And at the bottom, you have something called the torsion spectrums. And this is only finite. So think of them like I have finite copies of the sphere in some sense. So I have, for every prime, I will have a row. And I'm going to get here something that is labeled like this, P12, P21. I have these lines, Then I have P infinity 1, that's a 2, and P 2, 2, P infinity 2, then same thing here. And at the prime P, I have the same kind of figure. Oh, sorry, 1. And then all the way to P infinity P, and so on. This is P12, P13, and these are all connected to this. So it looks like this. And what the arrow here means is that, so these are the points of the spectrum, and what the arrow means is that the closure of this point is the opposite here, right? And if you see in the picture, the only closed points are actually the one sitting at the top, and the one at the bottom is dense, right? Its closure is the whole thing. And why is this like a very impressive result in homotopy theory? Is that this part here is actually encoded by the Morava K-theories of height, which height n. So if you know something about, if you've done a little bit of algebraic topology, you may have heard about singular homology. So at the bottom, we have singular homology with coefficients in the rational numbers. So that's why here you get all the torsion spectrum, because the rationals basically have to kill all torsion. And at the top, you have homology with coefficients in a finite field, in FP, right? And everything in the middle is sort of something new, well, new in a way, and they're encoded by the Morava K theory at the prime P, right, in each of these, and of height n. In height 1, this is maybe something that you know, it's topological K theory. So here we have like homology theories in the whole spectrum. And again, this is only for the finite, for the finite part. All right, that's what I was going to say about. Okay, but this is the thing, right? The Balmer spectrum can only be constructed for the compactly generated part, sorry, for the subcategory of compact objects. But what if we actually want to know something about the bigger category? So one cannot just associate a similar invariant as a Balmer spectrum to a big category. But we have a procedure by taking points in the Balmer spectrum and then kind of enlarge them to the big category. So that's this localization functor here. So I can take prime tensor ideals of the compact part and then just take its like all coproducts, or like, yes, generated by coproducts, cones, and all the whatever has to make sense with its triangulated structure. And I get this really big ideal. And well, okay. So these things are important because they turn out to be this special kind of subcategories that are called smashing. And well, that's the definition. But in a way, so in algebraic topology, in this category of spectra, you have SH. There's something called a Bowes-Field localization that is really just a functor that goes from the from the category into itself, and those are smashing are the ones that are given by take a space, a spectrum, and then you just take the smash product with the value of your localization at the sphere spectrum. So that's where the smashing comes from. And the kernel of this thing is the DS over there. Okay, so these smashing subcategories are actually, well, sorry, if I add the tensor ideal part, so I also ask them to behave like ideals with respect to the tensor product. I get a poset, right, with order inclusion, and it actually is a complete lattice, and well, Krause showed that this is actually a complete lattice, so that's a result of him. And not too long ago, Baldmer, Krause, and Stevenson showed that this lattice of smashing tensor ideals is actually a frame. All right. So, I mean, well, from the point of view of I guess, a topologist, if you get a frame, then I want to know if there is actually a space that realizes that frame as its frame of open subsets. But that's just like a curiosity from a topologist point of view. But there's actually a reason why the fact that this frame of smashing ideals being spatial is actually important. So it is related to the Balmer spectrum as follows. And well, I like this very much because one of the, well, for me, when I was learning the homotopy theory, one of the big obstacles for me to learn stuff is that the topic is very convoluted. It has like a lot of theory going on, and even like stating the important problems in the theory, it's very hard. Like, and if you heard about the telescope conjecture, or I mean, I think there was a Quanta magazine article on a telescope conjecture for spectra when, like a year ago, when four people actually proved that it did not hold for SH. But anyways, what I was trying to say is that in the language of TT geometry, sometimes these very hard statements become kind of easier to explain. So this is what I'm trying to do here. So I'm going to relate this a frame of smashing tensor ideals and the Balmer spectrum of the category. And they're related via what is called the telescope conjecture on a triangulated category. And so this is the setup. So I assume that my frame is spatial, right? And let me just denote by SPC to the S. And here, note that I can take away the C. No? So if this thing is spatial, then I actually get an invariant. I get a space, right, that I can associate to the full category. And well, so Valchin and Stevenson show that well, if this is spatial, then well, I can think about the points here as prime smashing tensor ideals. So there is a map, right, from the points of the space realizing the frame here, and I can go to the Balmer spectrum by just taking this smashing category, smashing tensor ideal, just restrict it to the compact part. And that will give me a prime tensor ideal that actually lives in the Balmer spectrum. And well, okay, just here I'm talking about continuity, right? So it matters what's the topology here. And this one is not exactly the one that Juan Omar showed us. I need to take its dual topology given by the Hochster's dual. It's just the duality I get for these kind of well, no, actually, you can take this for any space. All right, so I have this continuous map between the space realizing the smashing tensor ideals and the Balmer spectrum. And if I then want to say what the telescope conjecture is that that the map is a homeomorphism, right? So the telescope conjecture will hold if this map is a homeomorphism, if and only if, right? So in other words, what the telescope conjecture is saying that any smashing tensor ideal here comes from uniquely and sort of continuously from Balmer prime, right? So that's pretty nice. That's pretty nice to have such a statement. And the continuity or the topology is really related, right? It's not just that I have a bijection. I actually have a homeomorphism. All right. So that's why the smashing tensor ideals being spatial is sort of important. And this is what I'm saying, what I was saying before. The telescope conjecture is known to be false in some cases. What I was saying about the case of the homotopy category of spectra, like last year, 2023, this group of people showed that it does not hold. And the telescope conjecture in homotopy theory was the last. So some time ago, a professor called Doug Ravenel made a bunch of conjectures, made a bunch of questions, and a single person showed all of them, called Mike Hopkins, and he leaved only one, and that one was a telescope conjecture. And this was many years ago, and until recently, they didn't know if it was true. And well, these guys show that the conjecture is false in the homotopy category of spaces, and it's also known to be false in other cases. So this map is in general not a homeomorphism, but this thing can still be spatial, right? The fact that that map is not a homeomorphism doesn't have anything to do with the frame of smashing tensor ideals being spatial, right? And this is the topic of the project that I'm working with Angel and Juan Omar. And well, okay. The telescope conjecture tells us that the space that should actually, well, if the telescope conjecture holds, the space that should actually realize this is the Balmer spectrum, right? Because it will be a homeomorphism into the Balmer spectrum. But we know it's false in some cases, so you don't always get the Balmer spectrum. So what should realize this frame as a space, right? And okay, this is just take it with it's a bit delicate. We think it's true, but we haven't actually showed it. Well, this is true. When you have an Noetherian ring, the smashing tensor of ideals are just the same as fixed category. So the tensor is really not doing anything there, and these thick subcategories are actually well, it is a spatial frame because the telescope conjecture for some other reasons, but it all points out that the space that realizes this is something called the Ziegler spectrum, which has nothing, well, it's unrelated to the Balmer spectrum a priori and to smashing ideals and whatever. This spectrum actually comes from model theory in logic. And that's kind of one of the reasons that it's, well, hard for us to work on it, to understand it, because it's really an object that, well, the language it is written, everything here is very, very strange to us. So, okay, so this is sort of the motivating idea to our project, which is, well, in which other cases can the smashing tensor ideals be realized as the Ziegler spectrum of a big TT category? Okay, so to quickly just, I mean, I know I've given a lot of definitions. I'm going to give plenty more. And there's a lot of words, so all over, just bear with me. So okay. So the points here, and this is algebraic, so for most of you, it shouldn't be too far away. So the points here are well, isomorphism classes of indecomposable pure injective objects in our category. So pure injective just means, okay, so remember, when I have a category, I can take its Jonetta embedding, right, into functors out of T into some other category. But here, I'm going to restrict the functors to the compact part. I'm going to only see the full subcategory of compact objects. And again, this is a very nice category. we can think of this as just a model category. So what is a what is a pure injective in T? Well, something that under this Junet embedding maps to an injective object in this model sort of module category. Huh?
Here, what are your hypotheses on T?
Big TT. Yes. So rigid, compactly generated, tensor triangulated. So all the stuff. Okay. So I told you the Ziegler spectrum is a space, so it has a topology. And okay, so here comes another weird word, which is this. I told you this comes from logic, so there's like logic involved, and the closed sets on this like standard topology on the Ziegler spectrum are of this form. So are of those in the composable pure injectives that lie in a subcategory that is definable. So, okay. So new concept. So what's definable? So definable is as it is, something that I can define through a sequence of propositions of whatever, right? So this is a definition. So if I have a subcategory, and then I'm gonna consider the full subcategory of points in T that this thing vanishes for all F in that family. So let me just unpack what that thing's saying. So I have, well, I guess I just have to tell you what this home TF, and it's what it has to be, right? So I have a map, right, from say F from a compact object C to a compact object C prime, and then I can take its induced map from sorry, C, I guess it goes like this, right? Cx C X, and right, I can take this, I guess this one. So that's so this is F X. So I have those objects. So okay, so let me start again. So I start with a family of morphisms in the compact part of my category. So I start with these, and this is like the definable part. Those are like the propositions of my definable category, and I'm gonna take the objects that vanish under the well the I guess this is some sort of Jonetta embedding of F in every of these objects. Okay, so secretly you can think of definable things as like algebraic sets, right? So algebraic sets are sets that are cut out by zeros of polynomials, right? Or semi-algebraic sets that are cut out by a lot of relations, so I can say something like definable. I don't know why I'm speaking about this, but so definable in R, like definable sets in R are the same as semi-algebraic sets for the language less recall, bigger the recall, product, addition, and I think that's it. So I had these three symbols. I can make formulas out of these symbols. That's definable in R. That's actually the semi-algebraic sets. So in some sense, it makes sense that the Ziegler spectrum is appearing here because, well, Balmer spectrum kind of looks like a, well, like zeros of polynomials. No, so okay, so that's my intuition from it. I don't really know what the Ziegler spectrum is really, so I just think about this. All right, the frame of this, the frame. There's something weird here. The frame of the finable subcategory. Oh, yes, this is okay. So, sorry. Yes, it is. So what I wrote before here says that the definable subcategories actually are realized by the Ziegler spectrum, right? It's the closest of this space. So it's frames of well, dual up from opens of the Ziegler spectrum. Okay, so that's right. So the definable subcategories from a frame, and they're spatial by the Ziegler spectrum. Okay, so what has to do definable subcategories, and what I'm interested in are the smashing subcategories. Well, there's a theorem by Rose Wagstaff. So there's another presentment bijection between smashing tensor ideals and definable tensor ideals. So this is tricky. I don't really have here definable subcategories. I have definable tensor ideals. It's not the same, and unfortunately, it just doesn't restrict to the other one. Like I can't just restrict here to. So what I'm saying, I have this frame, but I can't just add the tensor and then get a frame, and then get realizability by some space. So it doesn't work like that. But this is like here's an example. So in general, the Ziegler spectrum will not realize the smashing tensor ideals. Here's an example. Just take the projective line and take its derived category. So the derived category of quasi-coherent sheaves on this thing. And well, you can consider the Ziegler spectrum, but then this set or space, whatever, has more points than smashing tensor ideals here. So it doesn't really realize what I'm looking for. But this is the motivating example to find like a suitable replacement for the Ziegler spectrum, and I will try to convince you that this actually this space, this category is realizable, and that we have a good candidate for it. So based on ideas of these two guys, Slavik and Prest, we introduce a new notion of purity, which is going to be called geometric purity. And so it's I guess, geometric. I don't know why it's really called geometric, but I guess it is what it is. And as a set, it will sit inside the Ziegler, or the pure injective in the composables. So okay, so here it goes. Okay, so we need one more notion, which is the one of pure mono. So again, if I have a morphism in T, I'm going to call it pure mono if under the geometric embedding, it's a monomorphism in the module category. Okay, now I'm going to consider this localizations. Just think of what Juan talked about, and to a Balmer prime, I can associate this localization function, where here, remember, this is like thickening. Well, maybe that's not the right word. Like enlarging P to the full big TT category. I'm going to call this T sub P. And okay, so this is our new definition. I'm going to say that a map or a morphism is geometrically pure mono if its image under every localization is mono in its respective module category. Secretly, you can think about what happens in sheaves. Like in sheaves, you can take stocks, and everything you can define it on the stock. And most of the times, or I guess kind of the beauty of it, that you can have properties from opens or the whole sheaf if you just look at properties on the stocks of the sheaf, right? So this is like the motivation here to look at the localizations. So it's I'm sort of thinking that the Balmer spectrum has a shift on it by categories. In this case, these localizations, but it's not really a shift or a pre-shift because we have categories, so things are more subtle. Okay, so what's a geometrically pure injective object? Well, okay, so this is a bit different of what we've seen, but so we take an object and if I have a mono, sorry, I'll say it again. I'm going to say that an object in T is geometrically pure injective if every geometrically pure mono in my category T splits. So all of these. Sorry, so all of these. Okay, it's a bit of a handful, this thing, but it works. So if, for example, my category is local, like 0 is a prime ideal, then geometric is the same as pure. Okay. Any pure mono in T is geometrically pure mono. And I think I had an idea. Okay, so this is sort of the picture that I have. So I have my localization functor. I have my Jonet embedding, both at the false category and at the prime P. And I get this map by other reasons. It's not just a restriction. It's a map I get because this has nice properties. So I always have this commutative diagram. So using this diagram, you can, I don't know, if something splits here already, it's gonna split over here because the splitting comes from here. So it all works out. So in particular, this implies that a geometrically pure injective object has to be pure injective. So this is the idea that I am going to construct a subset of the Ziegler spectrum that I can sort of have a good handle on it. Okay, and well, whenever you define something, you have to really check that it's actually something different. And well, this is actually different. So there are pure injectives that are not geometrically pure injectives. And you can verify this with our toy example, the derived category of P1. Okay, so here's the geometric Ziegler spectrum. So I'm going to consider the set of isomorphism classes of geometrically pure injective objects of my category T. I'm going to denote it G pinch. And as with the Ziegler spectrum, I'm going to say that a subset of this set of isomorphism classes is closed in the geometric Ziegler topology if it's of this form, where D is a definable tensor ideal. But just it's the analog with the Ziegler spectrum, but now with geometric purity encoded in it. Okay, so but here's a problem. I'm not saying that. I guess this is a weird way of phrasing it because I guess I'm saying that there's a topology out of this, but that's not true. I mean, well, we don't know if it's true. So in case it actually forms a topology, then we denote the resulting space as a CG tensor, and we call it the geometric Ziegler spectrum, if it is actually a topology. So our goal, right, is to give conditions on the localizations of the category to obtain spatiality from the full subcategory, from the bigger category. And so here's a result. So yeah, if I have a big TT category, and here's a strong assumption that the frame of the definable tensor ideals in the localization determines the closed subsets of the Ziegler spectrum, the one that I why are you nodding? The one that I defined before. For every prime, if I have this strong assumption on every prime, then the definable tensor ideals are a spatial frame, and they are realized by our geometric Ziegler spectrum. So in particular, the category is spatial. Okay, so this is a weird hypothesis, but maybe let me phrase it a bit differently. So instead of considering localization subprimes, I can take this restriction functors that Juan Omar defined. This is like also a localization, but with respect to a closed subset, so with respect to a complement of the open subset. And okay, here's a typo, where I have a set of opens of the the Balmer spectrum. Then I can formulate an analogous statement, which is now instead of asking for the frame of definable tensor ideals of the localizations, I ask that for the restrictions to an open cover, right? And then I have the same kind of statement. If that happens for every open in my cover of the Balmer spectrum, then I also get the category is definable, is spatial and realized by the Ziegler spectrum. And okay, so here's, okay, sure. So let's look at what happens with the toy example. So we have the derived category of P1, and then the specialty restrictions to that to those opens become, well, remember that P1 is the union of affine lines and is covered by affine lines, right? So what is this DP? I'm missing SP here, sorry. The point is that the question here comes that if this one here is definable, is realized by the Ziegler spectrum of this form. And what I mentioned before, when I introduced the Ziegler spectrum, it only asked if this one is this, if this thing wasn't Noetherian, right? So in these cases, this ones would be realized by the Ziegler spectrum, if whatever we said then actually holds what we think it does. So that would show that this one is spatial category, or its frame of smashing tensor ideals would be spatial. And I guess what we want to do is, well, I guess we have a sort of a program. Like if we have something happening at every localization, then what can we say about the bigger category? And well, in this case, we're using the Ziegler spectrum because it's what we know sort of how to handle. But you can ask some more of other kind of things. Juan Omar has some very nice ideas. And well, this is a work in progress. It's still making, we're still making new things. And I think that was all. Thanks.
Thank you, Bernardo. Is there any questions?
You mentioned some author called Krause.
Uh-huh.
Is he Gunther Krause?
No, Henning.
Oh, thank you.
What I understood about your results is everything is reduced to show that the closed Ziegler spectrum is a topology.
The geometric one, you mean?
Yeah.
Yes. So, I mean, uh,
The geometric case.
okay, so I told you that the geometric as a set, as a set, let me see. Oh, there it is. As a set, it sits inside the Ziegler spectrum. So, and this is really the same, well, it's similar to the definition of the bigger Ziegler spectrum. So you can ask if with this, well, if it is a topology, with this topology, it is a closed subset of the original Ziegler spectrum. And if it is, you will always get that this frame is spatial, yes.
So you are looking for conditions to get the topology.
To get the topology, yes.
And also, when you talk about injective objects, do you have enough injective objects? So something like every object you can embed it in an injective one? Or maybe there is a case in where some category where you don't have injectives, empty spectrum, is empty Ziegler spectrum. Can you have that? Sabelian.
The modulus.
You're working modulus.
Pure injective.
It's injective in mod TC.
Injective mode also? Oh, maybe Angel, do you have a Maltese theory in there? So can you and you have a bijection between indecomposable injective models and prime ideals?
I think in the fun case that.
In model theory, there is a famous theorem. Yes, you have a bijection between the spectrum of the ring and the decomposable injective model in the Noetherian case. Do you have here?
Yes, I think that's what we think. This actually realized the geometric Ziegler spectrum. And sorry, not the geometric, the honest Ziegler spectrum because of that. But the problem is that we don't know if that's a frame relation, that it respects order. So that's a thing that it's.
But in the fun case,
That's the affine case.
okay.
So we have a bijection, but we need this bijection to be induce an isomorphism of frames. So we need the order.
So nice. Thank you.
Thanks.
Yeah. No dijiste que era la completitud del telescopio.
Que una función fuera uno mismo.
Our next speaker is Jesus Efraín Pérez Terrazas. He's going to talk about data algebras, data algebras and reduction functors. Thank you.
And I don't know how to move this.
It should work now.
Okay. Well, I want to thank the organizers for the opportunity to attend this meeting. We all appreciate your hard work and kindness. And well, this talk is going to be in Spanish. Few parts are going to be in English, and there are no warnings before switching. Okay. So what I want to do is to chat about a proof of one single claim. And in order to do so, I'm going to give you a flavor about what data algebras are, how reduction functors works, and an application of radicals. And this application is related to Trujillo's talk. I'm sure it has a Gala connection. Hi. Well, I'm gonna walk through the. Okay. I want to walk through the first two subjects in order to explain the main ideas in the simplest way possible. And I want to just go straight as forward as possible to the claim. Okay. Now for some historical context, these ideas were developed by the Kiev School of Mathematics. In those days, this was named a bimodule with a coalgebra structure, box to short. And this was performed as matrix transformations. So it was known as reduction algorithms. And then later came Krolbubi. He was a game changer in this stuff, improved the theory, got new results, explaining in a better way everything about this theory. And the while and time theorem was proved by Dross with these techniques, but the version that the people studied and followed was that obtained by Krolbubi. Now the approximation to this theory that I'm going to use is the one developed by the Escuela Mexicana of Representaciones. Okay. Okay, so in this talk, K is always an algebraically closed field. The theory is more extended, is generalized more than this setting, but this one is easy to use and allows me to explain some ideas through drawings. Ok, entonces voy a estar considerando estas situaciones. Lambda siempre va a significar, siempre va a ser una K-álgebra de dimensión finita. Ya dije que esto va a ser algebraicamente cerrado. Y voy a estar considerando unos anillos que son los básicos para estar trabajando todo el tiempo. Entonces, van a ser productos directos de copias del campo o lo mismo agregando el anillo de polinomios localizado cuando lo necesite. ¿Ok? Entonces, pues por supuesto que aquí R es KX, R es KX. Cuando considero un álgebra de Carcaj, pues R se relaciona con los vértices. Aquí R es K, ¿no? Ok. Ahora, hay una parte que siempre vamos a estar trabajando con álgebras tensoriales, pero la voy a separar en dos porciones. Lo que normalmente se va a hacer es que se va a considerar una que tiene una propia graduación, que va a ser la parte de grado 0, y va a haber otra que va a ser la parte de grado 1. Y eso va a inducir una graduación sobre el producto tensorial que no es la usual, ¿no? Sino es una nueva. Entonces, bueno, en este caso, pues lo que tengo es W0 igual a 0, W1 igual a 1. Aquí en este caso, pues W0 es igual a 0. W1 es precisamente beta. Bueno, K beta. En este caso, W sub 0 se corresponde con los caminos de tamaño 1, es decir, con las aristas. Y W1 es simplemente 0. Perdón. Y en este caso, bueno, W0 se corresponde con K alfa y W1 se corresponde con K beta. ¿Ok? Y por supuesto que con lo que estoy trabajando, con lo que está trabajando es con el álgebra tensorial. Y en este caso, bueno, KX. En este caso es eh, KX beta. Aquí la álgebra tensorial es precisamente el álgebra de caminos. Y aquí, pues va a ser K alfa beta. ¿Ok? Ahora, como decía, lo que me interesa es la graduación que se va a estar trabajando. Esta es una álgebra graduada que tiene la graduación inducida por estas partes de aquí. Las flechas punteadas siempre representan algo de grado 1, las flechas llenas algo de grado 0. No significan relaciones. ¿Ok? Entonces, para este caso, lo que estamos llamando la parte de grado 0, inducida por esta graduación, que se corresponde a un álgebra. Entonces, en este caso, pues simplemente es KX, ¿no? Igual aquí es KX. Aquí es todo. No hay partes de grado 1. Entonces es el álgebra de Carcaj. Y aquí, la parte que se corresponde con el álgebra es precisamente K alfa. ¿Va? De esa forma. Ahora, la otra parte que es importante, les juro que no lo estoy tocando.
Es porque se quedó pegado ahí el láser.
Ah, entonces nada más tengo que... ahí está. Ok. ¿Cómo? Ok. Bueno, mientras, la otra parte que es importante es la parte de grado 1, ¿no? No sé qué escribí aquí. ¿Aquí de 0? Ok. Entonces la parte de grado 1 es 0. Aquí la parte de grado 1, va a ser, KX, beta KX. Aquí es 0. Y aquí es K alfa, beta K alfa. Entonces, esas son los elementos que determinan todo lo que ocurre sobre esta graduación inducida por la selección de bueno, en este caso, de las aristas. Ok. Muy bien. Entonces, estas álgebras tensoriales, lo que tengo que hacer es agregarles una diferencial, que lo que significa es una transformación RR bilineal que es de grado 1, ¿no? Simplemente va a subir de grado. Va a cumplir la regla de Leibniz y una cosa que es importante es que la diferencial del cuadrado sea 0. ¿Ok? Y entonces, bueno, de ella se ve por qué el nombre, ¿no? Esta cosa es una differential tensor algebra, pues precisamente porque es una álgebra tensorial con una diferencial. Ok. Ahora, por ejemplo, para esta, pues lo que puedo definir es que la diferencial sea 0. Entonces, automáticamente cumple todas las condiciones. En esta, también puedo definir que la diferencial sea 0 o puedo construir algo más complicado. Aquí también puedo definir que la diferencial sea 0. Entonces, todos estos se van convirtiendo en álgebras diferenciales tensoriales. Y en esta, bueno, me interesa que delta de alfa sea beta. Entonces, la extensión de eso es lo que voy a considerar. Entonces, todos estos son álgebras diferenciales. Ahora, por supuesto que esto está relacionado con el caso hereditario, pero precisamente las álgebras diferenciales, los boxes, se emplearon precisamente para poder lidiar con el asunto de el caso que no es hereditario. Entonces, si considero esta álgebra, esta álgebra de dimensión finita, esta es morita equivalente a una álgebra de caminos sobre un ideal admisible, es decir, este está en el cuadrado está contenido en el cuadrado del radical de Jacobson de esta álgebra. Y por el teorema principal de Wedderburn, bueno, pues esto se descompone en una parte semisimple y, y el radical de ¿no? Ok. Entonces, una construcción que se conoce como la dita álgebra de Dross, pues básicamente lo que hace es tomar esta información, sobre todo la que se corresponde con el cociente, y entonces, bueno, pues la parte semisimple va aquí, pero la parte semisimple, como estoy tomando una álgebra de caminos, pues en realidad es simplemente copias de K. Y este pizarrón baila, que es una barbaridad, ¿ok? Entonces, es de la forma que se está considerando. Ahora, cuando pongo J estrellita, pues lo que me estoy refiriendo son a los homomorfismos, como ese módulo derecho de JNS, también se puede hacer por la izquierda. Y básicamente lo que eso está considerando aquí es una forma de poder asociar. Ahora, la multiplicación, precisamente parte del asunto de por qué usar esto, es que la multiplicación del radical de Jacobson, pues como esto es un dual, lo que me induce es una comultiplicación sobre estos duales. Entonces, pues justo con eso puedo construir precisamente una diferencial que cumpla con esas propiedades. Entonces va a subir de grado y la regla de Leibniz lo que va a indicar, lo que está señalando, pues es que el producto es asociativo, el original, ¿no? Y además, pues lo que hay que destacar es que en estas operaciones, en la diferencial que va a aparecer asociada a esta álgebra de Dross, está codificado lo que hacen las relaciones sobre ese carcaj. Ok, ahora pues hay que definir la categoría de las álgebras, hay que decir quiénes son los quiénes son los objetos, quiénes son los morfismos, y por eso necesitaba definir quién es la subálgebra correspondiente a cada dita álgebra, porque entonces los objetos de la categoría son precisamente los módulos que se determinan por esa álgebra, ¿no? Entonces, pues, ¿quiénes son los objetos de aquí? Pues son los kx módulos, aquí también son los kx módulos, aquí son simplemente los módulos sobre el álgebra de caminos, y aquí son otra vez, son isomorfos a los módulos asociados a un anillo de polinomios, ¿va? Entonces, esos son los objetos. Ahora, los morfismos, esos son ya algo más diferente. Los morfismos se corresponden precisamente con con parejas de transformaciones lineales, ¿no? Entonces, cada vez que tenga alguna cuestión entre objetos de esta categoría, son parejas de homorfismos que tienen que cumplir esta propiedad de aquí, ¿va? Y esa propiedad de ahí, lo único que está diciendo es que esas parejas de morfismos lo único que está diciendo es que tengo dos formas de valorar. Y esas no tienen por qué coincidir. Entonces, la diferencial, lo que está contemplando F1 es qué tan lejos queda F0 de ser un homomorfismo, de ser un ahomomorfismo. ¿Vale? Entonces, la falta de conmutatividad del diagrama descansa en los hombros de F1. ¿Ok? Y bueno, se define cómo es la composición y todo ese asunto. El punto es que esto conforma una categoría. Ok. Ahora, hay ciertas propiedades que son bastante útiles cuando tiene uno necesidad de demostrar varias cosas. Una es que las álgebras sean triangulares, lo cual quiere decir que tienen una filtración que es muy buena con respecto a la diferencial. Pero bueno, todos los ejemplos considerados, en particular son álgebras triangulares. Ahora, ¿por qué quiero que sea triangular? Porque una vez que sé que es triangular, entonces, aunque las dos partes de un homomorfismo son indispensables, la primera parte pesa mucho, determina mucho lo que ocurre. Entonces, el homomorfismo es nilpotente, ¿no? Bueno, si es un endomorfismo nilpotente, sí, solo sí la primera parte es nilpotente. Entonces, aunque puedan ser muy raras las parejas que componen al morfismo, pues sé un montón de cosas, perdón, sé un montón de cosas una vez que sé qué pasa con la primera parte. La primera parte determina si son isomorfismos o no, y además se tiene la propiedad de que los idempotentes se escinden, ¿no? Entonces, esta es totalmente fundamental para poder trabajar como si fuera una categoría de módulos usual y para poder estudiar inescindibles y todo el asunto cuando uno lo ve cuando trata uno de pensar en términos de Krull-Schmidt. Ok. Y bueno, si agrega uno un poquito más de condiciones, todos aquí las cumplen, todos los ejemplos las cumplen. La subcategoría de los que son de dimensión finita, pues van a tener, van a conformar una categoría de Krull-Schmidt y entonces pues puedo dedicarme a estarlos clasificando. Entonces, todo funciona muy bien. Entonces puede uno pensar que estos son categorías de módulos con más morfismos, ¿no? Tiene los morfismos usuales, pero tiene otros adicionales que conllevan cierta información. El chiste es como determinar qué tan importante es la información adicional que lleva. Ok. Entonces, precisamente para pensar en qué ocurre con esa información o cómo irlo simplificando, se desarrollaron los funtores de reducción. Ok. Entonces, bueno, hay todo un procesamiento estándar para la mayoría de los funtores de reducción. Y entonces lo que dice uno, bueno, si tengo dos ditálgebras del tipo que sea, entonces pues uno define morfismos entre ellas. Y un morfismo entre ese tipo de ditálgebras, pues simplemente va a ser un morfismo de grado 0 con respecto a la graduación inducida. Que hace conmutar las respectivas derivaciones, ¿no? Eso es lo que cumple. Y una vez que se tiene un morfismo de esos, bueno, pues por restricción eso va a inducir algún funtor que va a ir de los módulos de acá en los módulos de acá. Entonces muchos funtores se construyen de esta forma. Ahora, es bastante técnico cómo se construyen, pero con dibujitos es más o menos fácil de explicar qué es lo que se hace, ¿no? Bueno, borro aquí. Ok. Entonces, si lo pienso como una serie de vértices y puntos y cuestiones de este estilo, como sea que lo quiera visualizar. Entonces, el funtor de eliminación de idempotentes me dice que si estoy considerando un módulo que en alguno de los espacios le corresponde un 0, entonces me puedo olvidar en los datos del carcaj de todo lo que toque esos ceros. Y que entonces, pues si quiero estudiar una subcategoría de módulos, bueno, de objetos de una cierta álgebra, que tiene 0 en ciertos puntos, pues me puedo olvidar de dónde están esos ceros. La puedo simplificar de una manera muy simpática. Ok, entonces ese es uno de esos funtores. Hay otro que es muy simpático, que es el que se llama reducción de un eje. Entonces, déjenme considerar este caso. En principio, pues este se ve bastante extraño, ¿no? Bueno, no sé, la primera vez que yo lo vi me pareció muy extraño. Pero aquí lo que está ocurriendo es que tiene uno parejas de morfismos. Entre objetos que cumplen, pues precisamente la condición de lo que está soportando, digamos, cuán lejos queda la primera parte de ser un morfismo de amódulos. ¿Ok? Entonces, lo que me dice la primera condición para construir este funtor de reducción es que de lo que tengo que preocuparme es de cuándo algo de aquí va a dar inyectivamente en algo de acá. ¿Vale? Entonces, en este caso, pues lo definí directamente así. Entonces, lo que me está diciendo es que aquí puedo tener un montón de morfismos, puedo tener kx módulos, pero en realidad esto es lo mismo que si borro la parte de grado 0 y la parte de grado 1 en la que está en correspondencia. Así que este carcaj que en principio se veía esta ditálgebra que en principio se veía tan extraña, pues en realidad simplemente es la categoría de espacios vectoriales sobre K. ¿No? Todo lo raro se fue de un solo golpe. Ok. Entonces, eso es lo que me dice el funtor reducción de un eje. Ahora, hay otro funtor que es el más, digamos, el más, en mi opinión, es el más importante de los funtores. Ese no sigue este esquema. Y básicamente lo que intenta es cómo voy a procesar cuando de todos modos obtenga algo, una diferencial de grado cero sobre algún objeto, sobre alguno de los caminos de grado cero. Y pues simplemente va a dar a cero. Entonces, me toco con un camino así, por alguna razón, delta de alfa es igual a cero. Entonces, este funtor lo que está haciendo es que me dice, considérate algún módulo sobre la subálgebra que se va a construir solamente con la parte que estás anulando. A lo mejor todo lo demás está lleno de un montón de morfismos y módulos, digo, de líneas y de caminos, pero solo concéntrate aquí. Y entonces, bueno, pues aquí yo puedo elegir, por ejemplo, a X como pues, los tres inescindibles que sabe uno que existen allá, ¿no? Entonces, cuando tengo esto, lo que va a hacer este funtor es convertir a esta flecha en tres puntos, los cuales van a estar relacionados por los homomorfismos entre ellos. Y agregaré flechas punteadas por cada morfismo, por cada endomorfismo que esté en el radical. ¿Vale? Entonces, si yo tenía, por ejemplo, un carcaj que hiciera una cosa así, ¿no? Y esta es la parte que se va a ir a cero. Perdón, esta es la parte que se va a ir a cero. Entonces, voy a tener tres nuevos puntos. Voy a tener este punto. Sí, de esa forma. Y aquí va a haber una nueva diferencial que, por ejemplo, lo que va a decir es que la diferencial aplicada en esta flecha, pues, perdón, aplicada en esta flecha, se va a convertir en esta seguida de esta, o en esta, perdón, o y esta se va a convertir en esta seguida de esta. ¿Vale? Entonces, va a llenar el diagrama de cuestiones con puntitos y con flechas punteadas, pero lo está simplificando en alguna forma. Está procesando lo que está en esta parte. Ahora, a lo mejor es un abuso esta metáfora. Una forma en que a mí me gusta pensarlo es, lo que está haciendo es que toma el módulo, lo apachurra, y los morfismos que hay en ese módulo que se corresponden con cosas en el radical, los expulsa como si fueran líneas punteadas. Bueno, entonces, espero no haber abusado ¿cómo se llama? De este intento de expresar con imágenes lo que hacen esos funtores, pero básicamente lo que tengo son, hasta ahí este momento, estos tres. Y me falta, bueno, y necesito pedir algunas propiedades adicionales para que se preserven cosas como la triangularidad o que los funtores que se van a construir sean fieles y plenos, pero esas son muy sencillas de obtener. Cosas como estas siempre las cumple. Ok. Y finalmente tengo otro funtor de este estilo, al que se le conoce como absorción de un lazo. Y básicamente lo que me dice es, bueno, si tú tienes aquí algo como esto, por decir algo, entonces tú puedes sustituir, tú puedes reconvertir tu ditálgebra llevándote este lazo a ser parte de R, ¿no? Lo bajas, digo, sigue teniendo grado cero, pero lo haces parte de R. Y vas a tener flechas similares, pero simplemente ahora vas a tener a alguien de esta forma. ¿Vale? Entonces, esa es la idea. tener esos funtores de reducción para poder procesar lo que está en esta parte. Ok. Ah, dije, ya me pasé de tiempo. No, ok. Bien. Entonces, bueno, intento explicar qué es lo que se hace, ¿no? Eh, cómo funciona a muy grandes rasgos eh, lo que hacía Dross, ¿no? Ok. Bien. Entonces, pues este tiene alguna forma complicada, pero al final de cuentas no deja de tener puntitos, eh, flechas llenas y flechas punteadas. ¿Va? Lo que me dicen los funtores de reducción es, bueno, si tienes alguna flecha llena que vaya a dar en alguna llena punteada, que en este caso no ocurra, pues las quitas, ¿no? Como tienes triangularidad, siempre tiene que haber algo que se vaya a cero. Así que, pues, si no puedes hacer nada aquí, pues a lo mejor puedes aplicar reducción por un bimódulo. Aquí se te va a complicar tu dibujo, tu diagrama. Se van a ir estos dos de aquí. Se te va a complicar tu dibujo, pero en el proceso de complicarlo, en términos de cómo se ve el dibujo, estás generando más puntos y estás simplificando los módulos. Entonces, si aquí ya tienes cómo aplicar reducción de un eje, pues lo haces. Si no, vuelves a aplicar reducción por un bimódulo. Pam, 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 te lo vas llevando. Y aquí hay una cuestión adicional que es que se va preservando hay una norma que va disminuyendo, ¿no? Es lo que permite hacer este tipo de argumento tipo inducción. Entonces, en algún momento me tiene que quedar a fuerzas, ya sea algo que ya sea manso salvaje, pero que se parece a un álgebra de Calcaj que se porta bien, o tiene que haber un lazo en algún punto del camino. Eso es forzosamente. Si empecé con una que es de tipo de eso se me olvidó. Aquí voy a empezar con una de tipo de representación infinito. ¿Ok? Entonces, una vez que tiene tipo de representación infinito, entonces cada vez que realice mi proceso, a fuerzas, en algún punto del camino me tiene que aparecer algo así. No sé cómo esté todo lo demás, no sé qué tan complicado esté la parte de afuera, pero lo que sí puedo asegurar es que hay una partecita dentro, hay una subálgebra que tiene que tener una hereditaria de tipo de representación infinito, ya sea dimensión finita o sea un lazo. A esa, si me aparece esta, le voy a aplicar la absorción de un lazo y entonces ya voy a obtener a alguien de esta forma. Y si no, bueno, yo ya sé que de todos modos de aquí yo puedo, tengo un funtor que manda objetos de aquí en objetos de acá. Módulos en módulos. ¿Está bien? Entonces, básicamente lo que estoy diciendo es que a partir de esta dita álgebra con la que se comenzó, entonces tengo diferentes álgebras en el proceso mediante funtores de reducción. Se van desarrollando todo el camino hasta que llego a algo que se parece a este de aquí. ¿vale? Entonces lo que voy a tener es un funtor que toma cosas aquí. Que toma módulos en esta parte y me los manda de aquí hasta acá, hasta la edita álgebra de Dross, ¿no? Es esta parte del camino. Ok, entonces ahora ya nada más me falta una última etapa para regresar a lo que quería estudiar, que es el álgebra con la que comencé. Entonces me faltan dos funtorcitos por tomar en cuenta. Entonces, la edita álgebra de Dross lo que tiene de simpático es que es equivalente con lo que se conoce como la categoría P1 lambda del módulo. ¿Y quiénes son estos? Bueno, esta es la categoría que se conforma por morfismos entre proyectivos. Entonces, estos son los objetos. La única restricción es que la imagen de F esté contenido en el radical del proyectivo de llegada. Y los morfismos acá pues simplemente son parejas que hacen conmutar el diagrama, ¿no? Entonces, esa es la categoría que está de este lado. Ok. Ahora, esa categoría que está allí, pues simplemente si aplico el funtor cokernel, esa por fin va a dar a lambda mod. Entonces, todo el proceso es, parto de una que es relativamente sencilla, sé que tiene que aparecer, y va a llegar hasta la original, en la que el problema que yo tenía aquí son las relaciones. ¿Va? Entonces, es todo el camino que está allá. Y bueno, se me olvidó, hoy se llama teta. Ok. Ahora, ¿qué tipo de funtores? Bueno, aquí existen asociadas unas estructuras exactas. Los funtores con esa estructura exacta que se les incorpora son funtores exactos. Así que de aquí hasta acá, esto es un funtor exacto. Perdón, hasta acá eso es un funtor exacto. Este es exacto derecho. Y todos son aditivos. Entonces, la composición de aquí hasta acá, por el teorema de Watts, se corresponde forzosamente con tensorizar con algún bimódulo adecuado. ¿Sabe? Entonces, esto simplemente fue tensorizar. Esa es la parte de aquí. Y debido a cómo son los funtores de reducción, yo sé que este bimódulo, por la derecha, es finitamente generado como KX módulo. ¿Está bien? Ahora, eso me puede dar algunos problemitas porque, bueno, podría ser que tenga partes de torsión. El bimódulo, y esas me complican que sea eh, que sea exacto. No solo exacto derecho, sino que sea exacto. Entonces, la ventaja aquí es que puedo localizar de manera adecuada, y entonces ya que localizo, lo que tengo es un nuevo funtor, simplemente lo localicé de la manera que me conviniese, y ahora este es exacto, ¿vale? Ya no solamente fue exacto derecho, es exacto. Y todavía puedo localizar más aprovechando que este es un dominio ideales principales. Así que si no me gustó el efecto de pues puedo localizar por algo todavía más, sigue siendo un polinomio finito, de tal manera que la estructura que tiene tiene una nueva estructura como de bimódulos, bueno, tiene su bimódulo de la siguiente forma, a través del radical de Jacobson de lambda. Y entonces, como bimódulos, voy a tener una sucesión de esta forma. Y la puedo poner de tal forma, si localizo lo suficiente, de tal manera que lo que tenga sean sumas directas como KX localizado, módulo derecho. ¿Vale? Entonces, puedo tener un bimódulo tan bonito como ese. Entonces, déjenme voy por fin a la parte de la aplicación. Ah, bueno, todavía, antes de eso, entonces lo que hay que observar es, este functor es fiel, perdón, no es fiel, desde aquí es pleno, desde aquí no es pleno, pero lo que me falta por considerar de los morfismos de acá, el chiste es que una vez que hace uno todas las cuentas de cómo se comporta de aquí hasta acá, lo único que hace es, o sea, los que me faltan, los que se corresponden con las flechas punteadas, lo que hacen es que toman lo que está en el tensorizado y lo manda a al mismo módulo, pero multiplicado por el radical. ¿Sí? Eso es lo que hacen las flechas punteadas. Lo que falta por considerar no afecta a la parte de aquí, sino a lo que queda cuando hago la cuenta de acá. Entonces, si comienzo con alguien, con un submódulo aquí, que, contiene todas las imágenes que provienen desde algún módulo, entonces, al tensorizar de aquí, solamente sumándole bueno, ahí sobra un tensor, pero sumándole ese va a contener a todo lo que se puede obtener como lambda morfismo. Ahora, eso me lleva a la aplicación a prerradicales, porque precisamente, bueno, como ya hay varias pláticas antes, voy a abusar un poquito de que ya son varias cosas conocidas, pero el punto es que como los prerradicales son los functores de la identidad, entonces, los submódulos que determina cada uno de ellos son cerrados bajo endomorfismos, son cerrados bajo morfismos desde otros objetos, de otros módulos, y en particular se pueden definir, esto es más general, pero bueno, ahorita voy a considerar totalmente invariantes, entonces se pueden considerar estos radicales. Ok, entonces, pues recordemos que esa es la situación con la que estaba trabajando. Y entonces lo que estoy diciendo es que si tenía a alguien que se comportaba como como un totalmente invariante, entonces de aquí se comporta como un totalmente invariante. Ahora, una forma simpática, bueno, a mí me pareció simpática, de expresar eso es, bueno, al hacer este caminito, pues simplemente puedo terminar el recorrido. Tomo el módulo que está aquí. Ese módulo me lo llevo hasta B1 tensor M. Hago el cociente por J de B1 tensor M. Y ese por la forma en que elegí las bases, ¿no?, para este bimódulo, pues eso simplemente va a ser de copias de M, ¿no? Entonces, de hecho, todavía más, pues simplemente al hacer esa asignación, lo que estoy haciendo es que estoy mandando los módulos de este lado en el anillo de módulos de esta parte, y la asignación, incluyendo lo que hace con los cocientes, es solamente la equivalencia de Morita usual. Así que eso me induce desde aquí hasta acá, y luego haciendo esto, pues me tiene que inducir una equivalencia de prerradicales. Ahora tengo que poner algo en medio. Y lo que puedo poner en medio, lo que puedo poner en medio, aquí se me escapó, aquí me falta la J, pero lo que puedo poner son los nuevos invariantes y ya sea los joints de los alfas o los mid de los omegas u otras opciones, pero eso me van a dar nuevos prerradicales que provienen precisamente de esta parte y que además yo sé que la asignación tiene que ser inyectiva porque cuando llegan a esta parte, es 1 a 1. Entonces, pues lo que se estaría probando, lo que se está probando, es que hay por lo menos tantos prerradicales aquí como los que hay acá. En otras palabras, si comencé con alguien que es de tipo de representación infinito, entonces los prerradicales no conforman un conjunto, es PR grande, ¿no? Y el regreso, pues esa consecuencia, bueno, ya está muy trabajado, pero bueno, es consecuencia de un teorema de Oslander acerca de álgebras de Artin de tipo de representación finita, ¿no? Entonces, pues ese sería el resultado y pues sería una de las implicaciones que comentaba ayer Rogelio que hacían falta, ¿no? Entonces, pues aquí estaría con algunos detallitos que no me había fijado en la redacción, pero aquí estaría la prueba de ese enunciado. ¿Me puedo seguir un poquito más? Ok, bien. Entonces, bueno, ese es principalmente el teorema que les quería platicar. Estas son técnicas que no son nuevas, digo, en principio, pues son lo de Drosses de los 70s, se han trabajado más, están mucho más actualizadas, se pueden hacer más cosas con ellas, y pues para dar una idea de lo que se trabaja actualmente, pues puse esta sección por si me daba tiempo. Entonces, ideas similares, con técnicas más avanzadas en situaciones diferentes, pues le permiten hacer otro tipo de cuestiones, ¿no? Entonces, pues por ejemplo, ya salió que este es uno que le estuvimos comentando mucho, que era mansos salvajes tiene un título muy al gusto de Leonardo, pero básicamente pues lo que estamos diciendo es que se cumple manso y salvaje para sistemas homológicos, ¿no? Esa es la cuestión. Hay una cuestión que se llama módulos genéricos, que también es uno de los aportes de Krully-Bouvier a la teoría, que lo que dice es que la propiedad de ser manso se puede caracterizar a través de cómo se comportan unos módulos especiales que se llaman genéricos, que digamos son, si yo quisiera caracterizarlos de una forma, pues una manera de imaginármelos es lo que pasa en los enteros, ¿no? Si yo quiero clasificar los enteros, bueno, los módulos abelianos finitamente generados, pues lo que tengo son los típicos diagramitas que recuerdan los tubos de las álgebras mansas. Y entonces en este caso, pues el que sería genérico serían los racionales, porque al final de cuentas el anillo de endomorfismos como grupo de los racionales, pues son los racionales. Entonces es una cosa que tienen longitud 1 sobre su anillo de endomorfismos, otras propiedades, pero básicamente lo que dice uno es que lo que observa acá en su cursito Buena Onda de Álgebra Abstracta 1, Y lo que pasa con los racionales, pues es una idea que se lleva uno a álgebras de dimensión finita. Entonces, pues también se está trabajando en probar que esos teoremas de Crowley-Booby funcionan también para sistemas homológicos. Y este está muy simpático. Recientemente se están haciendo cosas sobre cosas que se conocen como genéricos BRICS. Musaban y Paquet tienen artículos del 22, del 23 y del 24 sobre el tema. Y entonces una conjetura que ellos tienen es que, como aquí, ¿no? Va a haber bricks genéricos, que serían como las bocas de los tubos, una cantidad infinita. Sí, solo sí, va a haber un brick genérico, ¿no? Y entonces precisamente lo que se está demostrando usando esta técnica, ¿no? Nada más ajustando la antigüita, es que en efecto sí, la conjetura es cierta para el caso de álgebras masas, ¿no? Entonces, bueno, eso es lo que les quería platicar.
¿Hay alguna pregunta para él?
Gracias. Dijiste que la lambda de la cual partiste no necesariamente es hereditaria, ¿verdad?
No,
No,
es el
es
caso
cualquier
totalmente
lambda
general.
de dimensión finita.
Ajá, de tipo de representación infinito para que llegue hasta acá.
De dimensión finita y de tipo de representación infinito.
Sí.
Y la asignación phi, demuestras que es inyectiva intrínsecamente sin usar propiedades de toda la composición del funtor, ¿verdad? Porque te acuerdas que teníamos un resultado donde si el funtor era inyectivo en objetos y preservaba inclusiones, no estás usando nada de eso, ¿verdad? Nada más es la pura definición de la phi, ¿verdad?
Sí.
Y si te puedes regresar a la lámina donde defines la phi, creo,
¿Allí?
estas, sí.
Se barre un poquito. Aquí me falta agregarle la J.
¿La qué?
Multiplicado por J.
Ajá, por el radical de
Ajá.
Jacobson.
Sí, sí.
Y hiciste uso de un submódulo que mencionaste antes, que era el que tenía la propiedad de algo con las imágenes de los morfismos.
Ajá.
Ajá.
Lo que pasa es que cuando tengo el parametrizador, entonces los morfismos que están aquí, los que están en esta parte,
Es nada más la
digamos,
última parte, ¿verdad? La que tienes que arreglar de alguna manera.
sí.
Porque dijiste que era exacto desde la segunda categoría
Ujú.
hasta el final, es
Hasta el final.
exacto,
Es
¿verdad?
exacto, sí.
Ujú.
Pero el problema en principio que tenemos es, esta F de aquí se convierte en una parte de una pareja acá. Es un F0, 0,
Ajá.
¿no? Entonces, en esta parte de aquí, para poder asegurar que se comportan como totalmente invariantes, me falta poder tener control sobre la segunda coordenada. Ahora, la ventaja de estar acá es que, bueno, de que la diferencial sea 0, que esa es la parte importante aquí, sobre la parte que me interesa. Entonces, todos los morfismos de aquí se pueden escribir como sumas directas de morfismos. De esta forma. Eso en general no ocurre. Si uno está en otra parte de la cadena de morfismos, pues no necesariamente se puede separar en suma los morfismos en morfismos que tengan parte 0 y parte 0. Pero en este punto sí. Entonces, lo único que me falta ver es qué hacen los que están de este lado. Entonces, me lo voy llevando, voy haciendo la cuenta, hasta que veo que lo que hace los de esta parte es precisamente, cuando llego allí, este morfismo lo que hace aquí es tomar esto de aquí y mandarlo en este. Este es el submódulo que corrige la parte de ser totalmente invariante. Es lo único que hay que agregarle para que se siga comportando como si fuera parte de un preradical.
Luego me mandas el
Sí.
escrito. Sí.
Sí.
Bueno.
¿Alguna otra pregunta? Gracias.
Lo entrego acá.
thank you for staying here to the last conference, the last talk of MITAC. This talk will be given by Jose Armando Rosas Orozco about the frame-up congruent sets and any bonded lattice, its associated functor, and its place in other frames duality.
Okay. Well, thank you everyone for being here for the last talk. Thanks to the organizers for inviting me too. So this presentation is basically an abstract of what I'm doing for my master thesis. That's why it's a co-work with Angela and Anna. So yeah, let's begin. Yeah, so first, like a sort of an introduction. The motivation to construct this frame is the next one. Recall I'm going to use this for the category of bounded lattices and their respective arrows, and just pick whatever bounded lattice you like, your favorite one, and we're going to keep it fixed from now on. Okay, so as in any other structures, we have the congruences, which are just equivalent relations that also respect the order structure here, which is joins and meets, right? And we're going to denote by cong of lambda the set of all these equivalence relations. Okay, so it's from common theory that we can provide cong with a frame structure, but this structure is kind of troublesome to look out, especially all suprema. So instead, in my bachelor's thesis, we propose an alternate version, which is the frame of congruences, that I'm going to describe. And also in my bachelor's thesis, we use this frame to produce a sheaf representation for the lattice. And the structure of the frame actually affects a lot how that sheaf behaves. So for my master's, we decided to study more in depth what structure see as a frame, its properties. And we also want to know the exact category in which this frame lands, because it has some properties. So first, the frame. We're keeping our fixed lattice, lambda. And we're going to take the intervals, which are defined in the usual way. Just remember, this is any partial ordering, not necessarily the one we know. And we're going to see the whole lattice as the global interval, and all the singletons will be called the trivial intervals. And we're going to make sets using the intervals as members. And the two special cases that they're going to appear a lot here is the I, which is all the possible intervals, and the O, which is all the trivials only, right? So we're going to ask these sets to fulfill certain closures, which are the following. The first one is closure under similarity of intervals, which is asking that the set has both types of intervals of this form. The second one is that it has to be closed under takings of intervals, any subinterval. And the third one, omission, is kind of a transitivity property, right? And then, well, of course, the set must be non-empty, okay? And then we're going to say a set of intervals is basic if it satisfies the first two properties. And we're going to say it's a congruent set if it satisfies all three properties. Also, we're going to denote by B of lambda, all the family of all basic sets. And we're going to denote by C, the family of all congruent sets, okay? So here happens that B is closed under any intersection and union of basic sets. And C is closed on also under arbitrary intersections, but it's only closed under directed unions. Also, it results that the O and the I are congruent sets. So in particular, they're basic. And are also the bottom and the top element of C, respectively, and also for B, okay? Since they are also basic. So I'm not going to go too much into B, but we can prove that it has both a frame and a co-frame structure because it's all set theoretic. But the interesting property about this frame is that C appears as a quotient frame of B. To do that, we are going to define, well, just to see that these sets are actually important, it's that there is an isomorphism between C at Cong, where the relation is given as, I say, collapsing intervals. Because we're going to construct, for a congruence, we're going to construct their corresponding congruent set by the elements that the borders of the interval are congruent. Okay. So that's where the connection between the two appears. And for the quotient part, we want to define this operator. I also call it Cong because of the letters. That what does is take a basic set and consider all the intervals that could be partitioned in B. This means that exists this chain of elements that satisfies that each of these intervals is in B for all the indexes. So it results that Cong it's a nucleus on B, and the fixed family is precisely C. So that's how we provide C with a frame structure. And now we can focus on the sorry, focus on the frame of interest. So with that, C has a frame structure where the suprema are calculated by doing the basic union and they're applying the nucleus. And what's interesting is that C has the same negations, which are the pseudo complements, and the same implications of B. But C also has some extra properties. The first one that I think is very interesting is that there exists the least congruent set that has the interval AB as a member, and we're going to denote them with this notation, the angle notation. And what's interesting about these principal sets is that all of these are compact, and they generate the frame. Well, in particular, we can see the O and the I as these principal sets. So that makes this one in particular makes the frame compact, which is, I think it's interesting. And also the frame is algebraic because these principal sets generate any congruent set this way. And also, independently of the structure that lambda has, this frame is always special, which I think it's also very interesting. And to see that, the other interesting part is that the points are actually these, the points that we're going to use are actually these strongly prime members, which is a stronger notion of what we usually use as a point for a frame, because all these strongly prime elements are also points. And just a little a help for later. I'm going to construct this family for any interval, which is just the congruences that don't have the interval. Okay. So to prove spatiality, I prove this where I'm not going to prove it here, but this is a result from Birkhoff that makes proves the existence of sufficient strongly prime members on C, which give us the specialty, right? So, we obtain that our frame is not pointless. It actually has points. The most classical joke. Okay, so we also build the point space in the usual way. So the topology is the U sets where any U set is defined in this way is the points that aren't comparable with the congruent set that we take. So, well, because it's in the usual way, we always have that the space is T0 and sober because of this lemma and the typical counts. But if we remember, C has some compactness properties. And actually, these properties translate well to properties of S, thanks to this lemma that for each congruent set, if it is compact, then his corresponding open set is also compact in the point space. And moreover, any compact open of the topology of the point space has to come from a compact element of C, which is also useful because then we can say that S is compact and has a base of compact open sets. And just a quick sketch of the proof. We just need to recall that U preserves unions. C is algebraic. It's supreme generated by the principal sets, which are compact. And the special case of since it's the typical construction, the U set of the top element is the whole space, but this is also compact. So that makes the point space compact. And which all of this tells us is that the point space is almost coherent. But there's a problem there that we haven't managed to resolve yet with the intersection of the principal sets, which are the compact sets of the space. So, well, I call this the vertebral column because I want to use it as a base diagram for the rest of the work that we're doing. So for this diagram, I'm going to need all these categories. And when we do constructions in general, we want to see if it extends to a functor, if it is functorial. So that was one of the first questions that we asked in the master. And the answer is a yes, but it's complicated because, because we're going to make this functor, the functor C, to be to be covariant. And in the arrow point, we're going to, actually, this construction for the arrows comes from a more complicated path where I actually found this as the left adjoint of another arrow. So, but I'm going go there for here. And the problem is that we haven't we haven't determined yet if this CF arrow reserves meet. So that's why we just restricted to the category of joint complete similarities. Yeah, so what we have is so here we have the we have this functor, the congruence functor C, and we would like to make this functor go to the category of frames. But there's that problem with the arrows. So to try to solve that, because we can still connect this functor to frame, I'm going to use a couple of auxiliaries from category theory. That is that well, we have here we have the classic here we have our classic wait. We have the classic adjunction between frame and top, and the restriction to spatial frames and subspaces, right? So the category of spatial frames satisfies these two lemmas. So that helped me to get this proposition that the forgetful functor from here, this one, which is just the composition of this inclusion and this forgetful functor, has a left adjoint that we're going to call D. Well, actually, it goes to here. This is D, and there's the adjoint. Okay, so what this D functor does is construct the semi-point space of a joint complete similarities that I'm going to describe it with the respective arrows from the lattice to 2. And that also constructs a topological space using these new U sets. And the family mu of all these new sets is closed under arbitrary unions, but because we lack meets, it's not. It can be a base for a topology. So we're going to use it as a sub-base to produce a new topology. And what D does is take or similarities and send it to the topology of this new space, the semi-point space. And this gives us what we are going to call the free spatial frame on L. So here, one of the open problems is that the point space is a subset of the semi-point space. If we use the correspondence that we can also see the point space. Well, this. Because we can also see the points as the frame arrows from the frame to 2. But it has a subspace topology, right? Which is just the intersection of the subways with the set. But it already has another topology, the one that has as the point space of the frame, that also satisfies that is isomorphic to the original frame. But we think that these topologies might actually be the same, and that well, I haven't made the accounts yet, so that's why it's all in a probability. But we also think that the structure of this frame of C could make possible that actually these two spaces could be the same also. So to finish, all the works in progress that we have right now is, well, that in general, it's rather, it seems too difficult to give an explicit description of the principal sets. It appears a description when the lambda, the original lambda, well, I put A here, but when the original lattice is distributed, it helps solve some problems, but we want to see how many things we can get in the general case before concentrating on the distributed case. So that's why this is so difficult right now. And this problem also affects knowing what happens at the intersection of two of these principal sets. It doesn't necessarily give another one of these. That is, again, until we get to the distributed case for A. So yeah, that's also another open problem right now. We haven't also determined if what I just told you, that these CF arrows could present binary meets or not. And that also makes us to don't know if the functor lands of this category or if it actually lands on frame. And well, during this week, having some discussions with Angela and Anna, we just started to explore the idea of looking what other separation axioms could this, what the frame and the space could satisfy, because I haven't explored that yet. And well, that same problem also applies to the functor. We don't know any property in any categorical properties of the functor. We don't know if it could be faithful or full or anything like that. We don't know yet. So, well, the general approach to help us solve some of these questions, we're trying to move the frame to other perspectives, hoping to find an easier way to study it. And our big three approaches so far are precisely empty algebras, the Priestley L spaces, and also a thing that is called hating frames. And well, what are we trying to do is try to connect this diagram with the respective categories of these three topics. So there's probably, well, I like to call them blocks. So and this one kind of intersect each other. Yeah, we want to connect some more diagrams related to these three objects here. And well, the first idea for the empty block is that following Ranjita's work, we want to construct the associated empty algebra of C to have a new perspective, a new point of view. And well, just this week, I just heard from Ranjita that there's an equivalence between algebraic empty algebras and algebraic frames. So that made me think that I haven't obtained this empty algebra yet, but that makes me think that this hypothetical empty algebra might behave well and tell us more information about the frame. So the same goes for the Priestley L space block. We're also following Sebastian's work with this duality and these new spaces. And if you remember from this week, well, there's a duality between algebraic L spaces and also algebraic frames. So we think that if we construct C's L space, it might also be algebraic and compact. Yeah, so we want to use this L space too to see what other properties it could satisfy and translate it back to C using Priestley duality, just as Sebastian told us this week. And the last one, the hating frames block, is something that Gurams is working. And well, a hating frame is a frame that also satisfies that its compact elements form a hating subalgebra of the frame. This is in general. And well, following Gurams' work, hating frames play a role that is similar of what coherent frames do in the Sakya duality triangle. Well, the Priestley duality triangle is that we have and this is DLT. Yeah, well, this is the usual Priestley duality triangle between distributed lattices, Priestley spaces, and coherent frames. And a Sakya duality is for hating algebras. So we just restrict here to hating algebras. Here we would go to a Sakya spaces. And here is where hating frames appear. Yeah. That's why I say it's kind of the same role of coherent frames. And Guram also shows some generalizations of the Sakya triangle. When we relax these to things that Browvariant algebras and Browvariant similarities, that is just asking less properties from the lattice. And there is one that is related to algebraic frames that goes to a thing called point generalized Priestley spaces. This one, after reading a bit this week, seems to be the most difficult one of these three blocks. But I think we would like to construct also this new point generalized Priestley space for C. And well, we also want to observe what kind of information that new space could give us about the frame. Okay, so well, just to finish, this is all my references. Here's Ranjita's article, here's Sebastian's article. Here's for the results of the vertebral column, I use this article that I think it was also mentioned by Juan Omar during one of his talks. Here's the article of hating frames, and also some basic references to try to study, well, to help study point-free topology, the Johnstone, Picado, graded for lattice theory in general. This one is my bachelor's thesis because I use it a lot too. And these are some notes that Angel is making that also help me a lot too. So, well, thank you for your attention.
Is there any question for Armando? Yes.
But you mentioned that the basics are a frame and a coframe, right? Right? And and the assignment of the basic it's not a phantom
I don't know, I haven't explored that yet.
because you could maybe you called up functor the last
Yeah, that maybe
frame.
there could be a functor
It could be
using B, like for,
and explore what happens.
like something like that.
But it's you don't know if it's functional or not.
Yeah, I don't know yet, but it's also a thing that
You
I
wanna research?
just started to think about during this book too. Yeah, so, yeah, it could be interesting to see what happens there too.
Okay, good.
Mhm.
Congratulations.
Thanks.
So it's similar to this one, but inside of the congruence sets, you have the division sets.
But those
What is the theory that you get?
But well, the division sets only appear if the original lattice is an idiom, right? Yeah, because we're trying to work like in general. I haven't looked on the idiom context yet. Because for division sets you need suprema on A. That's why I haven't looked on that.
And if you ask that A is complete, everything works well.
Well, you mean like the sheaf representation?
Your functor C?
The functor C. Well, it should be because idioms in particular are lattices. So yeah, but I don't know precisely yet what happens in the idiom context either. That's also another open question that we're trying to solve. Yeah, there's a lot of work in progress here.
Thank you. Anyone else have a question for Armando? So let's take him. Now, thank you very much, everyone, for attend this first MITAC. I hope you had a good time, learn a lot, and I hope see you next year.
Thank you so much for coming, and I'm excited to have this meeting for first time. I hope that you have enjoyed every talk, every moment, and I hope that this is gonna be a good community and working pairs, working teams. So I hope to see you tomorrow and visit us. Thank you so much for coming. Muchas gracias a todos por venir. Para mí ha sido un placer poder contar con ustedes, que podamos construir esta comunidad y que proyectos como este que tenemos de CONACYT nos permita pues poder fomentar nuestra investigación, ¿no? Desde el principio, cuando comenzamos hace muchos años, en 2014, hace casi 10 años, con Mauricio y con Ángel en los seminarios que teníamos en el IMATE, en el IMATE y en la Facultad de Ciencias de la UNAM, pues siempre trabajamos con estos temas y después seminariábamos pues con el grupo de Pepe Ríos, aquí está presente Rogelio, los alumnos que se han ido formando, y la idea es que ustedes pues aprendamos a trabajar en comunidad y pues que las matemáticas se construyan de esta manera bonita, ¿no? Bueno, muchas gracias por venir. Gracias.
Yo solo quiero que todos demos un gran paso a Lisbeth, porque ella es la que ha hecho la gran parte de la organización, la parte dura de la gestión, la parte burocrática. Sí, creo que ella se merece, pues, el reconocimiento de que básicamente este evento existe por ella, ¿no? Por su esfuerzo y demás. Gracias.
I guess we still have coffee downstairs. Downstairs will be coffee.
See you. Thanks for coming.
¿Ustedes estaban oyendo?
Ah, ok.